Imagine being 16 years old and becoming trapped by a question that refuses to leave your mind. What would happen if you could chase a beam of light? At first, it sounds like the kind of question a curious teenager might ask while staring through a classroom window. Yet Einstein continued thinking about it for years, and the answer eventually forced humanity to reconsider some of its oldest assumptions about reality. It revealed that time does not pass at exactly the same rate for everyone. It showed that space is capable of bending, that matter contains enormous quantities of energy, and that gravity is connected to the structure of the universe itself. These ideas may sound distant from ordinary life, but they are already part of yours. Every time your phone determines your location using signals from satellites, Einstein's understanding of time helps make that calculation possible.
The sunlight warming your skin exists because a small amount of mass inside the sun is continuously transformed into energy. The atoms forming your body became understandable through scientific arguments that Einstein helped strengthen. Even the fact that you feel your own weight raises the same question that led him toward a new theory of gravity. Einstein did not begin with a vast laboratory or expensive equipment. He began with ordinary experiences that most people would have ignored. A compass needle moving without being touched. Clocks separated by great distances. A passenger sitting inside a train. A person falling from a roof, and a beam of light crossing an imaginary elevator. He looked at familiar things and noticed that the explanations beneath them were incomplete. Tonight, we will slowly follow the development of those questions and discover how they transformed both Einstein's life and humanity's understanding of reality. We will begin with the invisible force that fascinated him as a child. From there, we will follow him through classrooms, financial uncertainty, university disappointments, the quiet offices of the Swiss Patent Office, and the intense scientific debates that shaped the 20th century. Along the way, several questions will return again and again. How can you know that a distant clock is showing the same time as the one beside you? Why should every observer measure the same speed of light? What causes gravity? Are atoms physically real even when no one can see them? Does nature follow exact laws beneath everything we observe, or does chance exist at its deepest level? And how much of what you call common sense comes from reality itself, rather than from the narrow range of experiences available to the human body? Einstein spent his life following questions like these beyond the point where most people would have stopped. Some led to answers that changed physics almost immediately. Others produced disagreements that continued long after his death. A few remain connected to mysteries that scientists are still trying to solve. By the end of this journey, Einstein's story may feel less like the distant biography of a famous scientist and more like an invitation to examine the world around you with greater care. Because the universe he studied is also the universe surrounding you now. Its light enters your eyes. Its gravity holds you to Earth. Its atoms form your body. Its clocks measure every moment of your life. And the first step toward understanding it began when a small magnetic compass was placed in the hands of a curious child. Curiosity rarely announces itself with dramatic moments. More often, it begins so quietly that we only recognize its importance years later. A child notices the shadow of a tree slowly moving across a wall. Someone wonders why rain always falls downward instead of upward. Another child takes apart a clock simply because they want to understand what is happening inside. Most of these moments disappear into memory. They become small fragments of childhood, forgotten beneath school, work, and everyday life. For Albert Einstein, one moment never faded. Even decades later, after newspapers around the world celebrated him as the scientist who had transformed our understanding of the universe, he continued returning to the same childhood memory. It involved nothing more extraordinary than a small magnetic compass. At first glance, the instrument looked almost disappointingly simple. It rested comfortably in the palm of his hand. Beneath a thin piece of glass floated a narrow magnetic needle, free to rotate in any direction. Whenever the compass was turned, the needle slowly swung back toward the north. Every single time. Most adults hardly find that surprising. We learn from an early age that Earth has a magnetic field, and once we know the explanation, the mystery quietly disappears. For a child, however, the experience is entirely different. Nothing appeared to touch the needle. No string pulled it. No hidden mechanism pushed it. Yet something invisible filled the space around it and guided its motion with complete consistency. Years later, Einstein recalled that this simple experience left a profound impression on him. It was one of the first moments when he became convinced that the world contained hidden structures which could not be seen directly, but nevertheless govern the behavior of ordinary things. That idea never left him. Throughout his career, Einstein was repeatedly drawn toward realities that existed beyond immediate human perception. Invisible electric fields, invisible magnetic fields, invisible atoms, invisible space-time. Even gravity itself would eventually become something far more subtle than an invisible force pulling objects together. His greatest discoveries all shared the same pattern. Instead of asking only how something behaved, he wanted to know what unseen structure made that behavior inevitable. The compass answered none of those questions. It simply convinced one curious child that the visible world was only part of reality. Albert Einstein was born on March 14, 1879, in the German city of Ulm. Nothing about his birth suggested that he would become one of the most influential scientists in history. His father, Hermann Einstein, was an engineer and businessman whose electrical ventures alternated between optimism and financial uncertainty. His mother, Pauline Koch, came from a cultured family that valued education, literature, and especially music. She expected both of her children to receive a broad education, whether they appreciated it or not. One of those expectations was that Albert would learn to play the violin. At first, he treated the instrument like many children treat compulsory lessons, with little enthusiasm and a great deal of impatience. Only later did he discover what music would mean to him. Throughout his adult life, whenever a scientific problem refused to yield an answer, he often reached for his violin before returning to his equations. Friends remembered evenings when conversations about physics would suddenly stop. Einstein would begin playing Mozart or Bach, and after a while, he would quietly return to the discussion with a fresh perspective. To him, music and science were never completely separate worlds. Both depended on discovering harmony hidden beneath apparent complexity. Both rewarded patience, and both suggested that beneath the surface of the world lay patterns waiting to be understood. The same habit that allowed him to hear structure in music would eventually help him recognize unexpected order within the laws of nature. Let's return, however, to the young boy standing in his family's home with a compass in his hand. He still knew nothing about relativity,
Nothing about quantum physics, nothing about black holes, atoms, or the expanding universe. He had only one unsettling realization. Something invisible was shaping the world around him. And for the first time in his life, he wanted to understand what it was. His parents noticed that Albert was not quite like many other children. He was thoughtful, patient, and often preferred quiet observation to constant conversation. Family members later remembered that he sometimes paused before answering even simple questions, as though he wanted to be certain every word matched what he actually meant. Whether those memories became slightly polished over the years is impossible to know with certainty, but they reflect a characteristic that remained recognizable throughout his life. Einstein rarely accepted an explanation before he felt he truly understood it. If one step in a chain of reasoning seemed unclear, he would continue asking questions until the entire argument made sense. It was a habit that occasionally tested the patience of adults around him, but it also shaped the way he approached every scientific problem for the rest of his life. School, however, rewarded a different kind of student. In much of Germany during the late 19th century, education emphasized discipline, precision, and respect for authority. Lessons followed carefully planned routines, and students were generally expected to absorb established knowledge rather than challenge it. Memorization occupied an important place in the classroom, while curiosity often had to fit within the boundaries of the curriculum. Einstein found that environment difficult. He enjoyed mathematics because every conclusion could be demonstrated step by step. He enjoyed science because nature could always be questioned. Subjects that relied heavily on memorization without explanation interested him far less. This difference sometimes created the impression that he lacked discipline. The reality was more complicated. When a subject captured his imagination, he could concentrate on it for hours without noticing the passage of time. When he believed an exercise lacked real purpose, his attention disappeared almost immediately. Many talented students share that contradiction. The difference was that Einstein carried it into adulthood. He was never interested in collecting facts simply to possess them. Facts mattered because they revealed patterns, and patterns mattered because they hinted at deeper laws governing the universe. That distinction would eventually become one of his greatest strengths. Teachers naturally occupy an unusual position in stories about famous scientists. Once history knows the ending, it becomes tempting to divide every teacher into heroes who recognize genius and villains who failed to appreciate it. Reality is rarely so simple. Some of Einstein's instructors respected his ability, especially in mathematics and physics. Others found him frustrating because he questioned ideas that most students accepted without hesitation. A classroom built around efficiency can easily mistake persistent questioning for distraction. Einstein was not trying to be rebellious. He simply found it difficult to stop asking why. Why should nature obey these laws rather than different ones? Why should light behave exactly as physicists described? How could invisible forces act across apparently empty space? Those questions slowed lessons that were designed to move forward together. At the same time, they were quietly preparing him for a very different kind of work, one that depended less on mastering existing knowledge than on discovering where existing knowledge became incomplete. Outside the classroom, the world itself was changing with remarkable speed. Electricity was gradually leaving laboratories and entering everyday life. Cities expanded as electric lighting replaced gas lamps. Telegraph lines carried information across countries almost instantly. Engineers designed generators, motors, and power stations that would reshape modern civilization. The Einstein family experienced that transformation directly. Albert's father, Hermann, and his uncle Jakob operated electrical businesses during a period when the industry was still young and intensely competitive. Success often depended on staying ahead of rapidly changing technology, and financial security was never guaranteed. Some ventures looked promising before collapsing under economic pressure, while others survived only by adapting to new opportunities. For Albert, these business struggles had an unexpected consequence. Conversations about engineering, electricity, mathematics, and practical invention became part of everyday family life. Scientific ideas were not distant subjects discussed only inside universities. They appeared at the dinner table, in workshops, and in ordinary conversations about work. The invisible force that moved the compass needle belonged to the same unseen world that engineers were beginning to harness to illuminate streets, power factories, and connect distant cities. Without realizing it, Albert was growing up at exactly the moment when humanity was learning to control forces that previous generations could barely imagine.
His curiosity had found fertile ground. Before long, another influence would arrive that proved just as important as the compass itself. It would not be an invention. It would not be a scientific instrument. It would be a way of thinking about mathematics that transformed abstract symbols into a search for hidden truths. And it would permanently change how Albert Einstein looked at the world. The next turning point in Einstein's life arrived quietly. It was not a scientific discovery. It was not a remarkable teacher. It was a different way of looking at mathematics. Albert's uncle Jakob understood that many children lose interest in mathematics because they encounter it as a collection of rules instead of a process of discovery. Rather than asking his nephew to memorize formulas, he invited him to solve mysteries. He liked to compare algebra to a detective story. Somewhere inside every problem, he explained, there was an unknown quantity hiding from view. Since no one knew where it was, mathematicians simply gave it a temporary name. They called it X. The task was not to manipulate symbols for their own sake. The task was to follow the clues until the hidden quantity finally revealed itself. For Albert, this changed everything. Mathematics no longer felt like a language invented by teachers. It became a way of uncovering truths that already existed, waiting to be discovered. That simple shift in perspective stayed with him for the rest of his life. Even after he became one of the world's greatest theoretical physicists, Einstein never viewed mathematics as an end in itself. Equations mattered because they described reality. Every symbol represented something happening in nature, and every successful calculation brought him one step closer to understanding how the universe actually worked. This attitude would later distinguish him from many brilliant mathematicians. Some were fascinated primarily by the beauty of abstract structures. Einstein admired that beauty as well, but he was always asking a different question. What physical reality stands behind these equations? At around the same time, another important influence entered his life. The Einstein family regularly welcomed a young medical student named Max Talmud, later known as Max Talmy, to dinner. What began as ordinary family visits gradually developed into an informal education, unlike anything Albert experienced at school. Talmud quickly recognized that the quiet boy sitting across the table possessed an unusual appetite for difficult ideas. Instead of bringing children's stories, he brought books. Some introduced popular science, others explored mathematics. Still others opened the door to philosophy. One book, however, left an especially deep impression. It was a geometry textbook. Einstein later described his first encounter with Euclidean geometry with extraordinary enthusiasm.
Here was an entire logical system built from only a handful of simple assumptions. Every conclusion followed naturally from the one before it. Nothing depended on authority. Nothing had to be accepted simply because someone important had said it. If a statement was true, it could be demonstrated. For someone who instinctively questioned explanations, this was an exhilarating discovery. Knowledge did not have to be inherited, it could be rebuilt from first principles. That lesson became one of the foundations of Einstein's thinking. Whenever he encountered a difficult scientific problem later in life, he rarely began by asking what the leading experts believed. Instead, he tried to strip the problem down to its simplest form and rebuild it from the beginning. If every unnecessary assumption could be removed, perhaps the essential truth would reveal itself more clearly. This habit would eventually allow him to notice contradictions that generations of physicists had learned to overlook.
History often advances in exactly this way. Revolutionary discoveries do not always require entirely new facts. Sometimes they begin when someone looks at familiar facts and realizes that one old assumption no longer belongs. Outside the Einstein household, Europe was entering one of the most extraordinary periods of scientific and technological change in history. Factories expanded rapidly. Railroad networks stretched across the continent. Telephone systems began connecting cities. Electric power stations appeared in growing numbers, and laboratories produced discoveries at an astonishing pace. To many educated people, it seemed as though science was approaching completion. Isaac Newton's laws explained the motions of planets and machines with remarkable accuracy. James Clerk Maxwell had unified electricity, magnetism, and light into one elegant mathematical theory. Chemists had organized the elements into the periodic table. Engineers transformed new discoveries into practical inventions almost every year. There were still unanswered questions, of course, but many physicists believed they were merely small details waiting to be resolved. Albert could not have known that this confidence was about to be tested. He was still a teenager, spending his evenings reading mathematics, practicing the violin, and asking questions that often wandered far beyond the classroom. Yet he happened to be growing up at exactly the moment when the foundations of classical physics were beginning to crack. The cracks were still difficult to see. Most scientists believed the structure remained solid. Within a few decades, Einstein would help reveal that those tiny fractures reached far deeper than anyone had imagined. Before that could happen, however, his own life was about to change. Financial difficulties forced the Einstein family to leave Germany in search of new opportunities in northern Italy. Albert remained behind to finish his education. For the first time, he found himself separated from his family, living within a school system that had already begun to feel increasingly restrictive. The experience would soon push him toward one of the boldest decisions of his young life, a decision that placed his future at considerable risk, but ultimately led him toward the question that would define everything that followed. Albert's parents hoped that his separation from the family would be temporary. The plan seemed sensible enough. He would remain in Munich, complete his education, earn the qualifications expected of a promising young man, and eventually join them after finishing school. Instead, the separation made something unmistakably clear. The educational system no longer suited him. Einstein had never objected to hard work. What exhausted him was the feeling that genuine understanding often mattered less than unquestioning obedience. Lessons moved forward at a fixed pace. Students were expected to memorize, recite, and accept established conclusions. There was little room for following an unexpected question wherever it happened to lead. The more time he spent in that environment, the more convinced he became that it was pulling him away from the kind of thinking he valued most. Eventually, he made a decision that surprised almost everyone around him. He left. Walking away from school before completing the traditional course of study was not a small act of teenage rebellion. It placed his future in genuine uncertainty. Without the proper diploma, admission to a respected university would become considerably more difficult, and no one could promise that another opportunity would appear. For many young people, that uncertainty would have been enough to change course. Einstein accepted it. He joined his family in Italy, where life immediately felt different. Northern Italy offered a slower rhythm than the rigid routines he had left behind. Freed from the daily structure of school, he suddenly possessed something that had become surprisingly rare: time to think. He spent long hours reading mathematics and physics, revisiting ideas that interested him, instead of rushing from one assignment to the next. Without realizing it, he was teaching himself one of the habits that would define his scientific career: independent study. Many years later, Einstein would argue that education should not merely fill the mind with information. Facts are essential, he believed, but they become truly valuable only when curiosity gives them direction. Knowledge alone cannot produce discovery. Discovery begins when someone asks a question that existing knowledge cannot fully answer. Those months in Italy strengthened that conviction. Eventually, Einstein applied to the Swiss Federal Polytechnic in Zurich, one of Europe's leading institutions for science, mathematics, and engineering. His first attempt did not go as planned.
The entrance examination revealed an interesting contrast. His performance in mathematics and physics was exceptional. The examiners immediately recognized that he already possessed abilities well beyond those normally expected of someone his age. Other subjects told a different story. Languages, history, and several parts of the general examination were not nearly as strong, and his overall score fell short of the requirements for admission. From a distance, it can look like an embarrassing failure. In reality, the Polytechnic's director noticed something more important than the final result. Albert Einstein clearly belonged there. He simply needed a stronger general education before beginning university-level work. Instead of rejecting him completely, the director offered practical advice. He recommended that Einstein attend the cantonal school in the Swiss town of Aarau and then apply again the following year. The suggestion changed his life.
The school in Aarau could hardly have been more different from the classrooms he had left behind in Germany. Teachers encouraged discussion rather than memorization. Students were expected to think independently. Questions were welcomed instead of treated as interruptions. For the first time, Einstein experienced an educational environment that rewarded exactly the qualities that had previously caused him so much frustration. He flourished almost immediately. His confidence grew, not because the work became easier, but because understanding mattered more than simple obedience. It was also in Aarau that one question returned with unusual force. Imagine chasing a beam of light. The image had been with him for years, but now he began examining it more carefully than ever before. Suppose you could travel through empty space at exactly the same speed as a beam of light. What would you see? The question requires no advanced mathematics.
Anyone can imagine running beside another person or riding alongside a moving train. Extending that image to light seems almost natural. Yet, the moment Einstein tried to picture the situation clearly, everything began to unravel. According to James Clerk Maxwell's equations, light is an electromagnetic wave, and electromagnetic waves always propagate through space. They never remain frozen in place. Common intuition suggested one answer. Maxwell's theory suggested another. Both could not be correct at the same time. Most people would probably have set the puzzle aside and moved on. Einstein could not. The contradiction followed him through his classes, his reading, his walks, and his quiet moments of reflection. He did not yet know where it would lead, but he had learned something important about difficult questions. The most valuable ones rarely disappear. They wait patiently until the person asking them has learned enough to understand the answer.
By the time Einstein completed his studies in Aarau, the image of chasing a beam of light had become far more than a youthful curiosity. It had become the central thread running through his understanding of physics. He still had no revolutionary theory, no scientific publications, no reputation beyond a handful of teachers who recognized his unusual ability. What he possessed instead was something much harder to measure: the patience to live with an unanswered question for years without giving up on it. That patience would soon be tested in Zurich, where new friendships, unexpected setbacks, and countless conversations about physics would gradually transform one persistent question into one of the greatest scientific revolutions in history. In the autumn of 1896, Albert Einstein finally arrived at the Swiss Federal Polytechnic in Zurich. The institution attracted ambitious students from across Europe. Some hoped to become engineers, others mathematicians, teachers, or physicists. They came from different countries, spoke different languages, and brought different political and cultural traditions with them. For Einstein, it was the first place where he truly felt surrounded by people who shared his fascination with ideas. He enrolled in the program that prepared future teachers of mathematics and physics. Although the title sounded practical, the curriculum demanded a deep understanding of theoretical science alongside advanced mathematics. The freedom he had discovered in Aarau continued in Zurich, but freedom brought new responsibilities. No one forced students to study. No one monitored every hour of their day. Success depended largely on self-discipline. Einstein embraced that independence, though not always in the way his professors would have preferred. He attended many lectures, but not all of them. When he believed a course offered genuine insight, he worked enthusiastically. When he thought he could master the material more efficiently on his own, he often stayed away and studied independently. This habit made him an unconventional student. It also irritated several professors. Among them was Heinrich Weber, one of the Polytechnic's leading physics instructors. Weber had once enjoyed an excellent scientific reputation, but physics was changing rapidly. New discoveries in electromagnetism were transforming the field, and Weber was slower than many younger researchers to embrace these developments. Einstein noticed. He wanted to discuss Maxwell's electromagnetic theory, which represented the future of physics. Weber devoted relatively little attention to it. The difference may seem minor. It was anything but. Maxwell's equations described electricity, magnetism, and light as different expressions of the same underlying phenomenon. They were among the greatest achievements of 19th century science. Yet they also contained puzzles that no one fully understood. Those puzzles fascinated Einstein. When classroom discussions moved elsewhere, he continued studying Maxwell on his own. That decision would shape the rest of his career. Fortunately, university education extends far beyond formal lectures. Einstein found another invaluable resource in his classmates. One of them was Marcel Grossmann. Where Einstein was spontaneous and occasionally disorganized,
Grossman was methodical, dependable, and meticulous in his note-taking. His lecture notebooks became legendary among fellow students for their clarity and completeness. Einstein soon discovered that they were also extremely useful. Whenever he skipped lectures to pursue independent reading, Grossman's notes helped him catch up before examinations. Their friendship became one of the most important relationships of Einstein's early career.
Years later, Grossman would help him again, at a moment when he desperately needed both mathematical expertise and professional support. Another classmate would become even more significant. Her name was Mileva Maric. She had traveled from Serbia to study mathematics and physics at a time when very few women were admitted to advanced scientific programs. Reaching the Polytechnic had already required determination that many of her male classmates never had to demonstrate. She was serious, intelligent, and deeply interested in theoretical physics. Einstein quickly found in her someone with whom he could discuss scientific ideas for hours. Their conversations ranged across mathematics, mechanics, electromagnetism, and the newest developments in physics. They read scientific papers together, exchanged books, challenged each other's arguments, and spent long evenings debating difficult problems. Those intellectual exchanges gradually became a personal relationship.
Years later, historians would debate the precise extent of Mileva's influence on Einstein's scientific work. The surviving evidence leaves room for different interpretations, and scholars continue to disagree on some details. What is clear is that during these student years, she was one of the people with whom Einstein discussed physics most frequently. She belonged to the small circle of companions who understood exactly the kinds of questions that occupied his mind. Outside the classroom, Einstein developed habits that remained recognizable throughout his life. He enjoyed long walks. He loved sailing, despite never becoming particularly skilled at handling a boat. He played the violin regularly, sometimes alone, sometimes with friends. Above all, he talked. Physics was rarely far from the conversation. Ideas moved naturally from one topic to another. A discussion about mathematics could become a debate about electricity, then drift toward philosophy before returning to mechanics. For Einstein, these subjects were never isolated disciplines. They were different paths, leading toward the same destination, an explanation of reality. Yet beneath the outward freedom of university life, difficulties were beginning to emerge. Einstein's independent spirit, so valuable in scientific thinking, did not always translate into academic diplomacy. He challenged assumptions openly. He questioned professors when he believed they were mistaken. He cared far more about whether an argument was correct than about who had presented it. That attitude earned admiration from some classmates. It also created lasting tensions with members of the faculty. At the time, Einstein probably regarded these conflicts as little more than ordinary disagreements. He could not yet know that they would soon make finding employment extraordinarily difficult. Graduation was approaching. Most successful students expected recommendations from their professors, followed by assistantships that opened the door to academic careers. Einstein expected the same path. Instead, he was about to discover that intellectual independence can carry a price. The questions that had made him such an original thinker had also left him with remarkably few influential people willing to help launch his career. Graduation arrived in the summer of 1900. For most students at the Polytechnic, earning a diploma marked the beginning of a professional career. Professors recommended promising graduates for assistantships, laboratories hired young researchers, and the path toward academia, while never guaranteed, was at least visible. Einstein assumed that he would follow the same route. Instead, every door seemed to remain closed. His examination results were respectable,
particularly in mathematics and physics, but grades alone did not determine academic careers. Personal recommendations mattered just as much, and Einstein had spent several years frustrating some of the very professors whose support he now needed. He had challenged them in class, skipped lectures he considered unproductive, preferred independent study over carefully following the curriculum. From Einstein's perspective, he had simply been trying to learn in the way that suited him best. From the perspective of several professors, he appeared unreliable and difficult to supervise. Those impressions followed him after graduation. Assistantship after assistantship went to other students. Applications produced polite refusals or no reply at all. Weeks became months. The situation gradually turned from disappointing to worrying. Einstein had completed one of Europe's finest scientific educations, yet he could not find steady work. To support himself, he accepted temporary teaching positions wherever they became available. The appointments rarely lasted long.
Sometimes a contract ended after only a few months. Sometimes there were simply no more students to teach. He moved frequently, earned very little, and spent much of his time writing letters in search of permanent employment. Looking back, it is tempting to imagine this period as the familiar story of a misunderstood genius waiting for the world to recognize his brilliance. Reality was much less dramatic. No one believed Einstein had already transformed physics. He had not. He had published nothing revolutionary. Outside a small circle of classmates and teachers, he was virtually unknown. He was simply a young graduate struggling to begin his career. Yet these difficult months quietly strengthened another habit that would later become one of his greatest advantages. Because he lacked a university position, he also lacked the constant pressure to follow fashionable research topics or satisfy senior professors. His questions remained entirely his own. He continued reading Maxwell's theory of electromagnetism. He continued thinking about light. He continued returning to the strange contradiction that had first captured his imagination in Arau. What would happen if someone could travel alongside a beam of light? No answer satisfied him. Meanwhile, help arrived from an unexpected direction. His old friend Marcel Grossmann had never forgotten him. Grossmann's father knew people working within the Swiss federal administration, including officials at the Swiss Patent Office in Bern. Through those connections, he learned that a technical examiner's position might soon become available. At first glance, Einstein seemed like an unlikely candidate. He had never worked in a patent office. He possessed little practical experience evaluating inventions. His university career had hardly demonstrated exceptional respect for bureaucracy. Nevertheless, he applied.
The director of the patent office, Friedrich Haller, interviewed the young physicist personally. Haller quickly recognized that Einstein lacked formal experience in patent law. He also noticed something else. Einstein possessed an unusual ability to understand complicated technical ideas, identify the essential principle behind a device, and explain it with remarkable clarity. That talent mattered. A patent examiner did not simply read applications. He had to determine exactly what an inventor had created, distinguish genuinely new ideas from existing technology, and analyze mechanical and electrical designs with precision. Einstein could do that. In 1902, he received the position. The salary was modest but dependable. For the first time in several years, financial uncertainty eased. The patent office was not a prestigious research institute. It contained no great laboratories, no famous professors, no cutting-edge scientific equipment. Instead, Einstein spent his days examining inventions submitted by engineers and inventors from across Switzerland. Electrical systems, timing devices, communication equipment, mechanical designs. Every application demanded the same careful process. Strip away unnecessary details. Understand the central idea.
determine whether it truly differed from what already existed. The work was disciplined, analytical, and surprisingly well-suited to the way Einstein's mind naturally operated. Even more importantly, it left him something he had not possessed since leaving university. Evenings belonged entirely to him. When the workday ended, the real questions returned. The patent office paid his salary. Physics occupied his thoughts. The world's leading physicists worked inside famous universities, surrounded by laboratories, assistants, and established reputations.
One of the most important revolutions in scientific history was quietly taking shape in the apartment of an obscure patent examiner who spent his days evaluating inventions and his nights asking whether space and time might work differently than anyone had ever imagined. The stage was finally set. Within only a few years, Einstein would publish a series of papers that would permanently alter physics. Not one remarkable discovery, but an extraordinary sequence of breakthroughs that would later become known as his annus mirabilis, the miracle year. By the time Einstein settled into his routine at the Swiss Patent Office, he had reached an unusual position. Officially, he was a civil servant. Unofficially, he was becoming something else entirely. His working hours belonged to the patent office. His evenings belonged to physics. This separation proved unexpectedly valuable. University researchers were often pulled in many directions. They lectured, supervised students, attended faculty meetings, competed for promotions, and followed the priorities of their departments. Einstein had none of those obligations. When he returned home after work, he could devote himself completely to the questions that had occupied him for years. He was not trying to produce papers simply to build a career. He was trying to solve problems that genuinely bothered him. Around him, physics appeared stronger than ever. Newton's mechanics described the motion of planets with extraordinary accuracy. Maxwell's equations explained electricity, magnetism, and light in a single mathematical framework. Laboratories across Europe continued producing successful experiments. To many scientists, the foundations of physics looked complete. There were still unanswered questions, certainly, but most researchers believed they involved filling small gaps rather than rebuilding the entire structure. Einstein was becoming less certain. The more carefully he studied Maxwell's equations, the stranger they seemed. According to those equations, light always traveled at one specific speed in empty space. That conclusion looked perfectly reasonable until it was compared with Newtonian mechanics. Imagine standing beside a railroad track as a train passes. If someone walks through one of the train cars, passengers and people standing outside measure different speeds for the same person. Both measurements are correct because motion depends on the observer. The faster the train moves, the greater the difference becomes. This simple idea works beautifully for ordinary objects: a thrown ball, a running horse, a passing carriage. Everything follows the same basic principle. Why should light be any different? Common sense suggested that it should not. If someone chased a beam of light, shouldn't its speed appear lower, just as the speed of a moving train appears different to different observers? Maxwell's equations refused to cooperate. They did not allow light to slow down in that way. The contradiction was impossible to ignore. Either the familiar rules governing motion needed to change, or Maxwell's theory had to be incomplete. Most physicists searched for ways to preserve both. The leading explanation involved an invisible substance called the luminiferous ether. According to this idea, empty space was not truly empty. Instead, it was filled with an undetectable medium through which light waves traveled, much as sound travels through air or ocean waves move across water. If the ether existed,
Earth would constantly move through it while orbiting the Sun. That motion should have been measurable. In the late 19th century, physicists devoted enormous effort to detecting it. The most famous attempt was carried out by Albert A. Michelson and Edward W. Morley. Their experiment was extraordinarily sensitive.
If Earth drifted through the ether, light traveling in different directions should have taken slightly different amounts of time to complete its journey. The expected difference was tiny. Their instruments were designed to detect exactly such tiny differences. They found nothing. Again and again, the result remained the same. No measurable ether wind appeared. The outcome puzzled physicists across Europe. Some proposed increasingly elaborate explanations to preserve the ether. Perhaps the measuring instruments changed shape while moving through space. Perhaps matter itself contracted in just the right way to hide the effect. Each new proposal solved one difficulty while creating another. The theory became increasingly complicated. Einstein watched these developments with growing dissatisfaction. He admired elegant explanations. Whenever a theory required one special assumption after another, simply to survive contradictory evidence, he began wondering whether the problem lay somewhere much deeper. Perhaps physicists had been protecting the wrong idea all along. Perhaps the mistake was not hidden inside Maxwell's equations. Perhaps it was hidden inside the ordinary assumptions everyone made about space and time. That possibility sounded almost absurd. Space seemed obvious. Time seemed even more obvious. Everyday experience suggested that everyone shared the same present, that clocks measured one universal flow of time, and that distances remained fixed regardless of who observed them. Questioning those assumptions felt almost impossible because they appeared too fundamental to examine. Yet Einstein had spent much of his life doing exactly that. He had questioned invisible forces after seeing a compass. He had questioned accepted methods of teaching. He had questioned established physics while still a student.
Now he was beginning to question something even deeper: the nature of time itself. The answer would not arrive all at once. It would emerge gradually from a series of thought experiments, so simple that almost anyone could imagine them. A moving train, a railway platform, a flash of lightning, 2 clocks. With little more than those ordinary images, Einstein was about to demonstrate that some of humanity's most basic intuitions about reality had been misleading us all along. The solution did not appear in a single flash of inspiration. Einstein would later describe his work as the result of years spent thinking about the same problems from slightly different angles, returning to them again and again whenever a contradiction refused to disappear. Each attempt revealed another assumption that seemed perfectly reasonable until it was examined more carefully. Instead of searching immediately for new mathematics, he concentrated on something much simpler. He tried to understand exactly what physicists meant when they spoke about space, motion, and above all, time. The more he reflected on these ideas, the more he realized that people often used them without ever asking how they were actually defined. Everyone spoke confidently about 2 events happening at the same time. Clocks appeared to provide an objective answer, and daily experience reinforced the feeling that time flowed identically for every observer. Yet this confidence rested on an assumption that almost no one questioned. How do 2 distant clocks become synchronized in the first place? Imagine placing one clock in one city and another hundreds of miles away. If both clocks display the same reading, how can anyone be certain that they truly agree? Simply looking at them is impossible
because light itself requires time to travel from one place to another. Every observation arrives slightly delayed, and that delay must somehow be taken into account before any meaningful comparison can be made. For centuries, this complication hardly mattered. Human beings moved slowly enough that the difference was too small to notice. The development of railroads, telegraphs, and increasingly precise scientific instruments changed that situation. Engineers responsible for coordinating railway schedules, astronomers comparing observations from distant observatories, and physicists performing delicate experiments all depended on accurate measurements of time. What had once seemed like a philosophical curiosity was becoming a practical scientific problem. Einstein approached the question with remarkable discipline. Rather than accepting familiar language, he asked what procedures people would actually use to synchronize clocks. If a signal traveled between two locations at the speed of light, and if that speed remained constant, then a precise method for defining simultaneous events could be constructed. The important point, however, was that simultaneity would no longer be an obvious property of nature. It would become something defined through measurement. That distinction changed everything. Most people instinctively imagine a universal present stretching across the entire universe, as though there exists one enormous cosmic clock telling every observer exactly the same time. Einstein gradually realized that this picture depended on assumptions rather than evidence. Once the finite speed of light was taken seriously, different observers moving relative to one another could legitimately disagree about whether two distant events occurred simultaneously. This conclusion was so unfamiliar that it seemed almost impossible to accept. It contradicted ordinary experience so completely that many physicists initially resisted it. Yet the mathematics pointed consistently toward the same result, and every attempt to preserve the older intuition introduced additional complications that seemed increasingly artificial. To understand why, Einstein imagined a situation so ordinary that anyone could picture it without difficulty. A long train moves steadily along a straight track, while another observer stands on the railway platform, watching it pass. At the exact moment when the middle of the train reaches the observer, bolts of lightning strike both ends of the train simultaneously. The observer standing on the platform sees the flashes traveling equal distances toward the center. Since the light from both strikes arrives at exactly the same instant, the natural conclusion is that the lightning struck both ends simultaneously. Now consider the passenger sitting at the center of the moving train. While the flashes are racing toward the passenger, the train continues moving forward. As a result, the passenger moves toward the light coming from the front of the train, while moving away from the light coming from the rear. Even though light travels at the same speed in both directions, the flash from the front has a slightly shorter distance to cover, while the flash from the rear must travel a slightly longer one before reaching the passenger. The passenger therefore receives the front flash first and the rear flash a little later. Neither observer has made a mistake, neither observer suffers from faulty eyesight or inaccurate clocks. Both simply describe the same physical event from different states of motion, and both descriptions are equally valid. The unavoidable conclusion is startling. Events that are simultaneous for one observer need not be simultaneous for another. Simultaneity is not an absolute feature of the universe, but a relationship that depends on the observer's motion. Once Einstein accepted this idea, an astonishing number of contradictions began to disappear at once. The constant speed of light no longer stood in conflict with the principle that the laws of physics should be the same for every observer.
The puzzle that had occupied him since his student days slowly began to resolve itself, not because light had changed, but because our understanding of space and time had been incomplete all along. It was an extraordinary realization, and it led naturally to an even more surprising question. If observers moving relative to one another disagree about simultaneity itself, what happens to the measurements of distance and the passage of time? The answer would overturn ideas that had remained essentially unquestioned since the age of Isaac Newton, and would become the foundation of what we now call the special theory of relativity. Einstein completed the manuscript in the spring of 1905, but at the time there was little reason to believe that it would become one of the most influential scientific papers ever written. He was still employed full-time at the Swiss Patent Office, spending his days evaluating technical applications, and his evenings developing ideas that few people outside a small circle of physicists had even begun to consider. His name carried no special authority, and the journal that accepted the paper had no reason to expect that it contained the beginning of a scientific revolution. The paper bore the modest title, "On the Electrodynamics of Moving Bodies." Nothing in that title hinted at the magnitude of the transformation it would bring. There were no dramatic claims about overturning centuries of science, no declarations that Newton had been defeated, and no attempt to present the work as a revolutionary manifesto. Einstein simply followed the consequences of two principles that he believed should both be true. The first principle stated that the laws of physics must be the same for every observer moving at a constant velocity. No experiment performed inside a smoothly moving train, ship, or laboratory should reveal whether that system is moving uniformly or standing still. This idea had long been part of classical mechanics and was widely accepted. The second principle stated that the speed of light in empty space has the same value for every observer, regardless of the motion of the source or the observer making the measurement. Unlike the first principle, this one seemed to challenge ordinary intuition. Everyday experience suggested that velocities should simply add together. Yet Maxwell's equations consistently pointed toward a different conclusion. Einstein refused to sacrifice either principle. Instead, he asked what would have to change if both were accepted simultaneously. The answer was unexpected, because the contradiction did not lie in light itself. It lay in humanity's traditional assumptions about space and time. Once simultaneity became relative rather than absolute, a whole chain of surprising consequences followed, with remarkable mathematical consistency. Clocks moving relative to an observer would no longer keep time at exactly the same rate as clocks at rest. Objects moving at extremely high speeds would no longer retain exactly the same measured length along the direction of motion. Quantities that earlier generations of physicists had regarded as fixed properties of nature turned out to depend on the state of motion of the observer making the measurement. These conclusions often sound impossible when encountered for the first time, because everyday life provides almost no opportunity to notice them. Human beings move at speeds that are extraordinarily small compared with the speed of light, and under such conditions, the effects predicted by special relativity are so tiny that Newton's equations remain an excellent approximation. Bridges remain standing, planets follow predictable orbits, and baseballs travel exactly as common sense expects them to. Newton had not been wrong. His laws described a vast range of ordinary experience with extraordinary success. Einstein had simply discovered that those laws belonged to a larger and more general framework that became essential only under conditions involving enormous speeds or extreme precision.
Perhaps the most famous consequence of the new theory appeared only a few months later in another short paper. There, Einstein explored the relationship between mass and energy and arrived at an equation that has since become one of the most recognizable expressions in the history of science. E equals mc squared.
Its simplicity has often hidden its meaning. The equation does not merely provide a convenient way to calculate energy. It expresses a profound statement about the structure of reality itself. Matter and energy are not entirely separate entities. They are different manifestations of the same underlying physical quantity, and a very small amount of mass corresponds to an enormous amount of energy, because the speed of light is such an immense number. Einstein did not derive this relationship while thinking about nuclear reactors or atomic bombs, both of which still belong to the future. His purpose was entirely theoretical. He wanted to understand what necessarily followed from the new description of space, time, and motion. Decades later, physicists would discover that the equation explained the energy released inside stars through nuclear fusion and the immense power stored within atomic nuclei. But those practical consequences were not yet visible in 1905.
Even without those later developments, the year had already become extraordinary. Within the space of only a few months, Einstein published groundbreaking papers explaining Brownian motion, introducing the light quantum hypothesis to account for the photoelectric effect, establishing the special theory of relativity, and demonstrating the equivalence of mass and energy. Each paper addressed a different problem, yet together they reshaped several of the central foundations of modern physics. It is difficult to find another year in the history of science during which a single researcher, working largely in isolation, contributed so many discoveries of lasting importance. Even more remarkable is the fact that none of these achievements emerged from a famous university laboratory. They were developed by a young patent examiner who pursued fundamental questions after ordinary office hours because he could not stop thinking about them.
The scientific community, however, did not awaken overnight to celebrate the arrival of a new genius. Revolutionary ideas rarely receive immediate acceptance, especially when they overturn assumptions that have guided research for generations. Einstein's papers attracted attention, but they also raised difficult questions, invited skepticism, and demanded careful examination. Convincing the world's physicists would require much more than publishing a brilliant theory. It would require years of discussion, experimental evidence, and the willingness of other scientists to test conclusions that initially seemed almost impossible to believe. Although the papers published in 1905 were extraordinarily ambitious, Einstein did not expect the scientific world to accept them simply because he believed they were correct.
Physics had always advanced through argument, calculation, and experimental verification, and he understood that every important claim would have to survive careful scrutiny from other scientists who had spent their own careers working within very different assumptions. The first responses were cautious rather than enthusiastic. Many physicists recognized that the mathematical reasoning was internally consistent, yet consistency alone could not overturn decades of established thinking. Some readers admired the elegance of the arguments, while remaining unconvinced that nature actually behaved in such an unfamiliar way. Others found the conclusions so deeply at odds with ordinary intuition that they suspected some hidden mistake must still exist. This reaction was entirely understandable. Special relativity required scientists to abandon ideas that had appeared self-evident for centuries. Since the time of Isaac Newton, space had generally been treated as an unchanging stage upon which the events of the universe unfolded. While time flowed uniformly for everyone, independent of motion or location. These assumptions had worked so well for everyday mechanics that few researchers had seriously questioned whether they were fundamental features of reality or simply excellent approximations under ordinary conditions. Einstein's theory suggested that the assumptions themselves needed to be reconsidered. Instead of treating space and time as separate, independent entities, the mathematics revealed that they were intimately connected. Measurements of distance could no longer be separated completely from measurements of time because both depended upon the motion of the observer. Different observers could disagree about the duration of an event or the distance between 2 points, without either observer making an error.
The disagreement reflected the geometry of nature rather than any imperfection in the measurements. Even physicists who admired the theory often struggled with its philosophical implications. If time was not universal, what exactly did the word "now" mean? If observers moving relative to one another measured different intervals of time, could there still be a single present shared by the entire universe? Questions that had once belonged almost entirely to philosophy suddenly became central topics in theoretical physics, demonstrating that careful scientific reasoning could reshape concepts people had previously regarded as matters of common sense. One of the earliest and most influential scientists to appreciate the importance of Einstein's work was Max Planck. Planck was already one of Europe's leading physicists and had recently introduced the revolutionary idea that energy could be emitted or absorbed in discrete quantities, a proposal that marked the beginning of quantum theory.
Unlike many of his contemporaries, he approached Einstein's new theory with genuine curiosity rather than immediate resistance. Although he examined the arguments critically, he quickly recognized that they deserved serious attention and discussion. Planck's support proved enormously important. Scientific revolutions rarely succeed through brilliant ideas alone. They also require respected members of the scientific community who are willing to examine unfamiliar work honestly and encourage others to do the same. Planck's willingness to engage with Einstein's papers ensured that they reached a much wider audience than they otherwise might have, opening conversations that gradually spread through universities and research institutes across Europe. As more physicists studied the theory, another remarkable feature became increasingly apparent. Relativity had not introduced a long list of arbitrary assumptions designed to explain isolated observations. On the contrary, it had removed assumptions that no longer seemed necessary and replaced them with a simpler conceptual framework capable of explaining a much broader range of phenomena. This economy of ideas appealed strongly to scientists who believed that nature often revealed itself through surprisingly simple underlying principles. Yet Einstein himself regarded special relativity as incomplete almost from the beginning. The theory described observers moving at constant velocity with extraordinary success. But the real universe contains far more complicated situations. Planets orbit stars, rather than traveling forever in perfectly straight lines. Apples fall toward the ground. Elevators accelerate upward. Spacecraft change direction. Everywhere one looks, acceleration appears just as fundamental as uniform motion. Gravity, therefore, remained an unresolved problem. Within Newton's framework, gravity acted as an attractive force between masses separated by empty space, a description that had predicted planetary motion with extraordinary accuracy for more than 2 centuries. Einstein respected Newton's achievement immensely, but he could not ignore one unsettling question. If special relativity had required physicists to rethink their understanding of space and time, might gravity also require a deeper explanation than the one science had inherited from the 17th century?
That question did not emerge from abstract mathematics alone. It began with one of the simplest thought experiments Einstein ever imagined. An experiment involving nothing more complicated than a person falling freely through space. The idea seemed almost trivial at first glance, yet it would eventually lead him toward a completely new understanding of gravity, one that replaced invisible forces acting across empty space with the geometry of the universe itself. The insight that eventually transformed Einstein's understanding of gravity arrived so unexpectedly that he later described it as the happiest thought of his life. It did not emerge from a complicated calculation or an elaborate laboratory experiment. Instead, it began with an ordinary situation that almost everyone can imagine, yet very few people have ever examined carefully. Suppose a person is standing on the roof of a tall building and accidentally drops a ball. To someone watching from the ground, the explanation appears obvious. Gravity pulls the ball downward, causing it to accelerate until it reaches the Earth. This description had worked so well for more than 2 centuries that few physicists saw any reason to question it. Einstein approached the situation from a different perspective. Instead of imagining the observer safely standing on the ground, he imagined someone falling alongside the ball. During the brief interval before either object encountered the ground, both the observer and the ball would accelerate at exactly the same rate. Relative to one another, the ball would appear almost motionless, floating nearby as though gravity had somehow disappeared. This simple observation carried remarkable implications. If a freely falling observer could no longer detect gravity in the immediate surroundings, then perhaps gravity was not behaving like an ordinary force at all. The effect we normally describe as gravitational attraction might instead depend upon the observer's state of motion. Einstein continued exploring the idea by reversing the situation. Imagine a small elevator floating far out in deep space, so distant from every planet and every star that gravitational forces are effectively absent. If the elevator remains perfectly motionless, a person standing inside would experience weightlessness. A dropped object would simply drift beside them because nothing would pull it toward the floor. Now imagine that powerful engines begin accelerating the elevator upward with constant acceleration. From the perspective of the person inside, something extraordinary would happen. The floor would rise to meet any object released in the cabin, making it appear as though the object had fallen downward. Standing upright would suddenly require effort because the floor would press upward against the person's feet. Every familiar sensation associated with gravity would emerge, even though no massive planet existed anywhere nearby. Inside the closed elevator, the 2 situations would appear remarkably similar. One elevator rests motionless on the surface of the Earth, while gravity pulls everything downward. The other accelerates through empty space where gravity is absent. Without looking outside, no simple experiment performed entirely within the cabin could immediately distinguish between them. Einstein recognized that this resemblance was far too precise to dismiss as a coincidence. The equality between gravitational mass and inertial mass had long been known experimentally. Objects of different composition fall with nearly identical acceleration because the quantity determining gravitational attraction is proportional to the quantity determining resistance to acceleration. Newton had incorporated this fact into his theory with extraordinary success, but he had not explained why the 2 quantities should always be equal. Einstein suspected that their equality pointed toward a much deeper principle. Rather than treating it as an isolated experimental fact, he began asking whether it revealed something fundamental about the relationship between gravity and motion themselves. If acceleration and gravity could become locally indistinguishable under the right conditions, perhaps they were not separate phenomena after all. Perhaps they represented different descriptions of the same underlying reality. This idea became known as the equivalence principle, and it served as the conceptual foundation for everything that followed. It suggested that gravity should no longer be understood merely as an invisible force reaching across empty space. Instead, gravity might emerge naturally from the geometry of space and time, just as the apparent curvature of Earth's surface emerges even though a traveler standing in one small location may believe the ground is perfectly flat. Reaching that conclusion, however, required mathematics far beyond anything Einstein had used in developing special relativity. The geometry taught in school assumes that parallel lines never meet, and that the angles of every triangle always add up to 180 degrees.
Those familiar rules describe flat surfaces with remarkable accuracy, but mathematicians had already demonstrated during the 19th century that entirely consistent geometries could exist in which those assumptions no longer held. On curved surfaces, straight paths behave differently, triangles possess different angle sums, and distances cannot always be described using ordinary Euclidean methods. For several years, Einstein struggled to master these unfamiliar mathematical ideas. He understood the physical problem long before he possessed the mathematical language necessary to express it rigorously. And this period became one of the most demanding of his scientific career.
Unlike the breakthroughs of 1905, which had emerged from relatively concise papers, the search for a new theory of gravity required repeated false starts, abandoned approaches, and years of collaboration with mathematicians who understood geometries that had previously seemed far removed from physics. One of the most important people during this stage was his old university friend Marcel Grossmann. By then a distinguished mathematician, Grossmann introduced Einstein to the powerful methods of differential geometry that had been developed by Carl Friedrich Gauss, Bernhard Riemann, Gregorio Ricci Corbastro, and Tullio Levi-Civita. These mathematical tools provided exactly what Einstein had been missing: a rigorous language capable of describing curved spaces with extraordinary precision. Only then did the full picture begin to emerge. Space and time were not passive backgrounds upon which matter simply moved. They possessed their own geometric structure. And that structure could be altered by the presence of mass and energy. Objects moving under the influence of gravity were not being pulled by an invisible force in the traditional sense. Instead, they followed the straightest possible paths through a space-time whose geometry had itself been shaped by the matter it contained. It was an idea unlike anything physics had proposed before, and expressing it completely would require one of the most beautiful sets of equations ever written. Those equations, published in late 1915, would become the foundation of the general theory of relativity and permanently change our understanding of gravity, the universe, and the nature of space and time itself. When Einstein finally presented the general theory of relativity in late 1915, he was not merely proposing a revised explanation of gravity. He was asking physicists to abandon an image of the universe that had shaped scientific thought since the time of Newton, and to replace it with something far less intuitive, but far more comprehensive. According to the new theory, gravity was no longer a mysterious force acting invisibly across empty space. Instead, matter and energy altered the geometry of space-time itself, while planets, stars, and every other object simply followed the natural paths created by that geometry. The idea was elegant, but elegance alone could never establish a scientific theory. However beautiful the mathematics appeared, it would have little value unless its predictions agreed with observations of the real universe. Einstein understood this perfectly. His equations had to explain phenomena that Newtonian gravity already described successfully, while also accounting for observations that had resisted explanation for decades. One of those long-standing puzzles involved the orbit of Mercury. Astronomers had measured the planet's motion with increasing precision throughout the 19th century and found that its orbit behaved almost exactly as Newton's theory predicted. The word almost, however, concealed an important problem. Mercury's elliptical orbit slowly rotated over time, a phenomenon known as the precession of the perihelion. Most of that motion could be explained by the gravitational influence of the other planets, but a tiny portion remained unexplained despite years of increasingly careful calculations. The discrepancy was extraordinarily small. Measured against the enormous scale of the solar system, it amounted to only a few dozen arc-seconds per century, an angle so tiny that most people would struggle even to imagine it. Yet science often advances by paying close attention to precisely these kinds of small inconsistencies. A theory may appear nearly perfect while concealing a deeper flaw that becomes visible only through the most careful observations. Einstein applied his new equations to Mercury's orbit and discovered something remarkable. Without introducing arbitrary corrections or additional assumptions, the equations produced exactly the unexplained amount that astronomers had been measuring for years. A problem that had resisted solution within Newtonian mechanics emerged naturally from the geometry of curved spacetime. For Einstein, this result was deeply satisfying. It suggested that the theory was not merely mathematically consistent, but physically meaningful. The equations were revealing something genuine about nature rather than simply describing an elegant, abstract model. Even so, one successful calculation could not settle the matter. A theory of gravity intended to replace Newton's had to survive far more demanding tests. Einstein therefore turned his attention to another prediction, one that seemed even more astonishing than the motion of Mercury. If gravity represented the curvature of space-time, then light itself should respond to that curvature. This conclusion deserves careful consideration because it initially appears contradictory. For centuries, gravity had been associated with weight and mass. Stones fall because they possess mass. Planets remain in orbit because they attract one another through their mass. Light, however, has no rest mass, so under the traditional picture, there seemed little reason to expect gravity to influence its path in any significant way. General relativity approached the problem from an entirely different direction. Light does not travel because gravity pulls on it like a rope tugging an object through space. Instead, light always follows the straightest possible path available within space-time. If space-time itself becomes curved by the presence of a massive object, such as the Sun, then the straightest possible path also becomes curved. From our perspective, the beam of light appears to bend, even though it is simply following the geometry of the universe. The prediction was extraordinary because it transformed gravity from something that acted only upon massive bodies into something that shaped the behavior of everything moving through space-time. Testing the prediction, however, presented a formidable challenge. Under ordinary circumstances, the brilliant light of the Sun completely overwhelms the faint starlight passing close to its edge. Even if gravity bent those distant rays, astronomers could not measure the effect because the stars themselves disappeared in the Sun's glare. Only during a total solar eclipse, when the Moon blocks the Sun's bright surface, do those background stars briefly become visible, close enough to the Sun for their apparent positions to be measured. Einstein realized that nature itself had provided the necessary experiment.
If astronomers photographed the same stars during a total eclipse and then compared their positions with photographs taken when the sun occupied another part of the sky, any systematic shift might reveal whether their light had been deflected while passing near the sun. The required measurements were extraordinarily demanding. The predicted deflection amounted to less than 2 arc-seconds, an angle so small that it pushed the observational techniques of the early 20th century to their limits. Temperature changes, atmospheric turbulence, imperfections in photographic plates, and tiny mechanical distortions in telescopes all threatened to overwhelm the signal astronomers hoped to detect. Nevertheless, the challenge was worth attempting because the outcome carried enormous significance.
If the observations agreed with Einstein's prediction, they would provide powerful evidence that gravity truly reflected the curvature of space-time, rather than an invisible force acting across empty space. If they disagreed, then one of the most ambitious scientific theories ever proposed would require serious revision. By this point, Einstein's work had begun attracting increasing attention within the international scientific community, but he had not yet become a household name. Outside physics, very few people recognized him, and even among specialists, his new theory remained the subject of vigorous discussion rather than universal acceptance. That situation was about to change dramatically, not because Einstein sought publicity, but because the natural world itself was preparing to deliver the first great observational test of general relativity.
When the opportunity finally arrived after the First World War, the results would propel both the theory and its creator into worldwide fame. Although the story of that famous eclipse would later prove to be considerably more complex than the simplified version that often appears in popular accounts. Although Einstein became closely associated with relativity in the public imagination, the next great scientific revolution was developing along a path that neither he nor anyone else had anticipated. Ironically, Einstein himself had helped lay part of its foundation years earlier, through his work on the photoelectric effect. Yet many of the conclusions that later emerged from quantum theory left him deeply dissatisfied. The disagreement was never a simple conflict between an aging scientist and a younger generation. It reflected two fundamentally different ways of thinking about the nature of reality, and both sides recognized that the questions at stake reached far beyond the boundaries of physics. The origins of the debate stretched back to a growing collection of experimental results that classical physics struggled to explain. As researchers investigated atoms, radiation, and the behavior of light with increasing precision, nature repeatedly refused to conform to expectations that had worked so successfully at larger scales. Phenomena that seemed straightforward in everyday experience became unexpectedly subtle when examined within the microscopic world. Einstein had already demonstrated his willingness to challenge established ideas whenever the evidence demanded it. In 1905, he proposed that light, traditionally understood as a continuous electromagnetic wave, could, under certain circumstances, behave as though it consisted of discrete packets of energy.
This bold hypothesis explained the photoelectric effect, in which light striking a metal surface ejects electrons only if its frequency exceeds a certain threshold. Classical wave theory alone could not account for the observations, whereas Einstein's proposal provided a remarkably simple explanation. For this work, rather than for relativity, Einstein would eventually receive the Nobel Prize in physics. The distinction often surprises people because relativity dominates popular discussions of his career. At the time, however, the experimental evidence supporting the photoelectric effect appeared more firmly established, while general relativity was still relatively new and continued undergoing careful observational examination. The Nobel Committee therefore recognized the contribution that had already demonstrated clear experimental importance, without attempting to settle ongoing scientific discussions surrounding relativity itself.
Meanwhile, quantum theory continued advancing at extraordinary speed. Niels Bohr introduced a new model of the atom that combined classical mechanics with emerging quantum ideas. Louis de Broglie suggested that matter itself possessed wave-like properties. Werner Heisenberg developed matrix mechanics, while Erwin Schrödinger formulated wave mechanics using a very different mathematical approach. Although these methods initially appeared unrelated, they soon proved mathematically equivalent, revealing a powerful new framework for describing atomic behavior. The deeper physicists explored this framework, the stranger it became. According to the developing quantum theory, many physical quantities could no longer be predicted with absolute certainty before measurement. Instead, the mathematics often yielded probabilities describing the likelihood of different outcomes. This did not simply reflect incomplete knowledge or inadequate instruments.
Within the standard interpretation that gradually emerged, probability appeared to be woven into the structure of nature itself. Einstein found this conclusion profoundly unsettling. Throughout his scientific career, he had searched for elegant laws governing apparently complicated phenomena. Even when observations appeared confusing, he believed that a deeper level of order ultimately existed beneath them. Quantum mechanics, by contrast, seemed to suggest that uncertainty represented an unavoidable feature of reality, rather than a temporary limitation of human understanding. The disagreement centered on a remarkably subtle question. When physicists calculate the future behavior of a system, are they describing what nature actually is, or are they merely describing the probabilities of what observers may eventually measure?
The distinction may sound philosophical, but it carried enormous scientific consequences because it determined how researchers understood the relationship between mathematics, observation, and physical reality. Einstein never denied the extraordinary success of quantum mechanics as a predictive tool. Its calculations repeatedly agreed with experiments, often to astonishing precision. He admired the brilliance of the theory and respected many of the scientists responsible for developing it. His concern lay elsewhere. He wondered whether the theory represented the final description of nature or merely an extraordinarily successful approximation that concealed a deeper deterministic structure still waiting to be discovered. These questions became the subject of some of the most famous scientific discussions of the 20th century. At conferences throughout Europe, Einstein and Niels Bohr debated the conceptual foundations of quantum mechanics with remarkable intensity.
Einstein repeatedly proposed carefully designed thought experiments that he believed exposed weaknesses or contradictions within the standard interpretation. Bohr responded by analyzing each example in painstaking detail, arguing that quantum theory remained internally consistent even under Einstein's most demanding challenges. Observers who attended these discussions often remarked upon the extraordinary respect both men showed one another, despite their profound disagreements. Neither regarded the debate as a personal contest. Each understood that the outcome would influence humanity's understanding of reality itself. Einstein's objections forced advocates of quantum mechanics to sharpen their arguments, while Bohr's responses revealed strengths in the theory that had not always been fully appreciated beforehand.
Scientific progress emerged not because one side immediately defeated the other, but because sustained criticism compelled both positions to become clearer and more rigorous. Perhaps the most famous expression of Einstein's discomfort appeared in a private letter to the physicist Max Born, where he wrote that he could not believe God plays dice with the universe. The remark has often been quoted as though it represented a rejection of modern physics, yet its original meaning was considerably more precise. Einstein was not making a theological argument. He was expressing his conviction that the deepest laws of nature should ultimately possess an underlying order that did not depend fundamentally upon chance. Quantum physicists replied that nature was under no obligation to satisfy human preferences for certainty. Experiments continued supporting the predictions of quantum mechanics with increasing accuracy, even when those predictions seemed to violate ordinary intuition. Rather than disappearing, the tension between Einstein's philosophical expectations and the empirical success of quantum theory continued growing throughout the following decades. Eventually, Einstein would formulate one final challenge, together with Boris Podolsky and Nathan Rosen, that would become one of the most influential papers in the history of modern physics. The argument appeared to expose a profound incompleteness in quantum mechanics, but instead it opened an entirely new chapter in our understanding of entanglement, locality, and the surprising connections that can exist between particles separated by enormous distances. That debate would continue long after Einstein's death and remain central to quantum physics even today. The paper that Einstein published together with Boris Podolsky and Nathan Rosen in 1935 began with a question that appeared almost technical, yet it would eventually reshape the direction of modern physics. The three authors were not trying to demonstrate that quantum mechanics produced incorrect numerical predictions, particles that interacted briefly before moving apart in opposite directions. According to quantum mechanics, certain properties of the two particles remained correlated, even after they had become widely separated. Measuring one particle immediately allowed an observer to predict the corresponding property of the other with perfect certainty. Einstein found this deeply troubling. If measuring one particle instantly revealed information about another particle located far away, then one of two uncomfortable conclusions seemed unavoidable. Either information somehow traveled faster than light, contradicting one of the central principles of relativity, or the quantum description omitted deeper variables that already determined the outcome before any measurement occurred. Einstein regarded the second possibility as far more plausible. He believed that physical properties should exist independently of whether someone happened to observe them. The moon, he famously joked in conversation, did not appear in the sky only when someone looked at it. Reality, in his view, possessed an objective existence that science gradually uncovered rather than created through the act of measurement. Many of his colleagues accepted a different interpretation. According to the view associated primarily with Niels Bohr and the Copenhagen school, quantum mechanics did not describe hidden properties waiting to be discovered. Instead, it described the probabilities of possible measurement outcomes, and asking for additional details beyond what the theory provided might simply be asking a question that nature itself did not answer. Bohr responded to the Einstein-Podolsky-Rosen paper almost immediately. His reply did not dispute Einstein's mathematical reasoning. Instead, he argued that Einstein's expectations about physical reality relied upon concepts inherited from classical physics that could no longer be applied without modification in the quantum world. Measurements, Bohr insisted, could not be separated completely from the experimental arrangements used to perform them. The observer was not magically creating reality, but the conditions under which observations became meaningful were far subtler than classical intuition suggested. The disagreement was extraordinarily difficult because both sides agreed on the experimental facts. Both accepted the mathematical success of quantum mechanics. Both demanded logical consistency. Both believed that science should describe an objective universe. What separated them was their understanding of what a successful scientific theory ought to explain. For Einstein, the goal of physics was to reveal the underlying mechanisms responsible for observable phenomena.
even if those mechanisms remain temporarily beyond experimental reach. A theory that relied fundamentally upon probability felt incomplete, because probabilities usually reflect incomplete knowledge rather than the deepest level of reality. For Bohr, the purpose of physics was more modest and, in some respects, more practical. A successful theory should provide precise predictions for every experiment that could actually be performed. If those predictions consistently agreed with observation, then demanding additional hidden explanations might simply exceed what science was capable of establishing. Neither position could easily eliminate the other. The debate therefore continued for decades, encouraging physicists to examine increasingly subtle experiments that previous generations had never imagined performing. For many years, the Einstein-Podolsky-Rosen argument remained primarily a philosophical challenge, because no available technology could test its deepest implications directly. The situation changed dramatically in the 1960s, when the Northern Irish physicist John Stuart Bell discovered a remarkable mathematical result that transformed the discussion from philosophy into experimental science. Bell demonstrated that any theory based upon local hidden variables had to satisfy specific mathematical relationships that became known as Bell's inequalities. Quantum mechanics predicted that carefully designed experiments could violate those inequalities under certain conditions. For the first time, researchers possessed a concrete way to distinguish between Einstein's preferred type of explanation and the predictions of quantum theory. The experiments required extraordinary precision and remained technically difficult for many years. But improvements in lasers, detectors, and quantum optics gradually made them possible. Beginning in the late 20th century and continuing into the 21st, increasingly sophisticated experiments consistently produced results in agreement with quantum mechanics while violating Bell's inequalities under conditions designed to eliminate alternative explanations. These observations did not prove that Einstein had been foolish. On the contrary, his challenge had forced physicists to formulate sharper questions, develop more powerful mathematical tools, and design experiments of unprecedented sophistication. Even when nature appeared to favor quantum mechanics, the path toward that conclusion existed largely because Einstein had insisted that the foundations of the theory deserved relentless scrutiny. This pattern appeared repeatedly throughout his career. Einstein rarely accepted an explanation merely because it seemed successful. He preferred to search for the assumptions hidden beneath every theory, believing that genuine understanding required more than accurate calculation. Sometimes that instinct led him toward revolutionary discoveries, as it had with relativity. At other times, as in his disagreement with quantum mechanics, it led him toward conclusions that later evidence did not fully support. Yet even those disagreements became remarkably productive because they exposed weaknesses in existing arguments and inspired entirely new areas of research. Today, concepts such as quantum entanglement, quantum cryptography, and quantum computing all trace part of their intellectual history to questions Einstein never stopped asking. He did not live to see many of these developments, but the conversations he began continue shaping some of the most active fields of modern physics. By the middle of the 20th century, Einstein had become far more than the author of a few influential scientific papers. He had become an international symbol of scientific curiosity itself, recognized around the world not only for his theories, but also for his unmistakable appearance, his thoughtful public statements, and his willingness to engage with some of the most difficult moral and political questions of his era. Those later years would reveal another side of Einstein's life, one that cannot be understood solely through equations, because it unfolded against the backdrop of war, dictatorship, exile, and the immense responsibilities that accompanied global fame. As Einstein's scientific reputation continued to grow, the world around him was changing with alarming speed.
The political instability that followed the First World War gradually gave way to economic crises, rising nationalism, and increasingly aggressive authoritarian movements. During the 1920s, these developments remained troubling but uncertain. By the beginning of the following decade, however, they had become impossible to ignore, especially in Germany, where Adolf Hitler and the National Socialist Party were rapidly gaining power. Einstein had never confined himself entirely to scientific questions.
Throughout his life, he spoke publicly about education, international cooperation, civil liberties, and the dangers of militarism. Although his political views evolved over time in response to changing historical circumstances, he consistently believed that scientific progress alone could not guarantee a better society. Knowledge, in his view, always carried ethical responsibilities, and those responsibilities became far more difficult to ignore as Europe moved toward another catastrophic conflict. His public visibility made him an unusually prominent target. By the early 1930s, Einstein had become one of the most recognizable scientists in the world, while his Jewish background, international reputation, and outspoken political views attracted increasing hostility from the Nazi movement. National Socialist propaganda portrayed modern theoretical physics, particularly relativity, as an example of what they called Jewish science, a label that had nothing to do with scientific evidence and everything to do with anti-Semitic ideology. Rather than debating equations, critics attempted to discredit both the theories and the people associated with them through political and racial attacks. Einstein understood that the situation was becoming increasingly dangerous. When Adolf Hitler became Chancellor of Germany in 1933, Einstein happened to be traveling abroad. After carefully considering the political situation, he decided not to return. The decision marked a permanent turning point in his life. The country in which he had been born, educated, and established much of his scientific career was no longer a place where he believed freedom of thought or personal safety could be guaranteed. The consequences reached far beyond one individual. Universities throughout Germany lost many of their leading scholars, as Jewish scientists, political opponents of the regime, and others facing persecution sought refuge elsewhere. Among those who left were physicists, mathematicians, chemists, physicians, and philosophers, whose work had helped place German science at the forefront of international research. Their departure transformed the global scientific landscape, strengthening institutions in Britain and the United States, while dealing a lasting blow to Germany's intellectual community. Einstein eventually accepted a permanent position at the newly established Institute for Advanced Study in Princeton, New Jersey. Unlike an ordinary university department, the institute was created specifically to support fundamental research by giving scholars the freedom to pursue difficult questions without the immediate pressures of teaching large classes or meeting extensive administrative obligations. It offered precisely the kind of intellectual environment in which Einstein had always worked most effectively. His daily routine remained surprisingly modest despite his extraordinary fame. Visitors often expected to encounter someone consumed by celebrity or surrounded by elaborate ceremony. Instead, they found a man who preferred quiet walks, long conversations, simple clothing, and hours spent thinking about mathematical problems. He continued playing the violin, welcomed discussions with colleagues and students, and devoted much of his time to the search for a unified field theory that might combine gravity and electromagnetism within a single mathematical framework. This final scientific ambition occupied him for decades. Einstein hoped that the same instinct for conceptual simplicity that had guided the development of relativity might reveal an even deeper level of order beneath the known forces of nature. Physics had already demonstrated remarkable unity by showing that electricity and magnetism formed different aspects of one electromagnetic phenomenon. General relativity had explained gravity through the geometry of spacetime. Einstein wondered whether these achievements represented only intermediate steps toward an even more comprehensive description of the universe. The scientific community, however, was moving in a different direction. While Einstein concentrated on geometric approaches to unification, younger physicists increasingly focused on quantum field theory and the rapidly expanding understanding of elementary particles. Experimental discoveries continued accumulating at an astonishing pace, revealing a subatomic world far richer and more complicated than anyone had imagined during the early years of the 20th century.
New particles appeared, new mathematical methods emerged, and research priorities gradually shifted away from the questions that had become the center of Einstein's later work. This divergence has sometimes been portrayed as evidence that Einstein had become isolated or unwilling to accept new ideas. The historical record presents a more nuanced picture. Einstein followed developments in quantum physics closely, corresponded with many of its leading researchers, and understood the remarkable predictive success of their theories. His reservations concerned their conceptual foundations rather than their practical achievements. He continued believing that a deeper and more unified description of nature remained possible, even if he never succeeded in discovering it. Whether that hope was ultimately realistic remains a subject of discussion among physicists and historians alike.
What cannot be disputed is the extraordinary persistence with which Einstein pursued questions that he considered fundamental. Success never convinced him that inquiry should end, and failure rarely persuaded him that an important question had become unworthy of further thought. Even after transforming physics more profoundly than almost any scientist before him, he approached each new problem with the same patience that had characterized the curious child staring at the mysterious movement of a compass needle many decades earlier. As the 1930s gave way to the Second World War, however, events beyond the laboratory began forcing scientists to confront choices unlike any they had previously faced.
For Einstein, those years would bring one of the most difficult moral dilemmas of his entire life, because the discoveries that had expanded humanity's understanding of nature were becoming increasingly entangled with technologies capable of destroying civilization on an unprecedented scale. By the summer of 1939, the international political situation had become increasingly unstable. Germany had already absorbed Austria, occupied Czechoslovakia, and was moving steadily toward a conflict that many feared would soon engulf Europe once again. At the same time, developments in nuclear physics were revealing possibilities that only a few years earlier would have seemed almost unimaginable. Experiments carried out by researchers across Europe suggested that the nucleus of the atom contained enormous stores of energy, and the recent discovery of nuclear fission raised an unsettling question that scientists could no longer dismiss as mere speculation. Could that energy be released in a rapidly multiplying chain reaction? For physicists, the question was fascinating because it opened an entirely new field of research. For governments watching the political situation deteriorate, however, it carried an additional and deeply troubling implication. If such a chain reaction could be controlled, it might eventually provide a powerful new source of energy. If it could not be controlled, it might instead produce a weapon, unlike anything the world had ever seen. Einstein was not the person who made these discoveries. He had not participated in the experiments that revealed nuclear fission, nor was he directing research into nuclear weapons. Nevertheless, his famous equation describing the relationship between mass and energy had become an unavoidable part of the scientific background.
The equation explained why nuclear reactions could release such extraordinary amounts of energy, even though Einstein himself had developed it decades earlier while pursuing entirely theoretical questions about relativity. Several physicists who had fled Nazi-controlled Europe became increasingly concerned that German scientists might attempt to build such a weapon before the Allied nations fully understood the danger. Among them was the Hungarian physicist Leo Szilard, whose imagination had long been occupied by the possibility of self-sustaining nuclear chain reactions. Szilard believed that political leaders needed to understand the situation quickly, but he also recognized that his own name carried little influence outside scientific circles. Einstein's name, by contrast, was recognized throughout the world. During the summer of 1939, Szilard visited Einstein at his vacation home on Long Island.
Together with fellow physicists, he explained the recent discoveries in nuclear physics and outlined the possibility that uranium might eventually be used to produce extraordinarily powerful weapons. Einstein listened carefully, asking questions about the scientific evidence before considering the broader political implications. The discussion led to one of the most consequential letters in the history of science. Addressed to President Franklin Delano Roosevelt and signed by Einstein, the letter warned that recent developments in nuclear physics justified serious attention from the United States government. It suggested that Germany might also pursue similar research, and recommended that American officials maintain close contact with scientists investigating uranium. The letter did not launch the Manhattan Project by itself, as popular accounts sometimes imply. Its historical importance lay in helping draw political attention to a possibility that several scientists already regarded as increasingly urgent. The American program that eventually produced the first nuclear weapons emerged through many decisions involving governments, military organizations, industrial resources, and thousands of researchers working over several years. Einstein played no direct role in that project and was never invited to participate in its secret research, partly because government officials considered his political associations unsuitable for work requiring the highest security clearance. This distinction is worth emphasizing because it is often misunderstood. Einstein's scientific discoveries contributed to the theoretical understanding of mass and energy, but he neither designed the atomic bomb nor worked on its construction. His involvement consisted primarily of lending his reputation to a warning that other physicists believed political leaders needed to hear before it was too late. As the Second World War progressed, scientific research became increasingly intertwined with military priorities. Laboratories that had once pursued fundamental questions about nature now found themselves contributing to radar technology, cryptography, aviation, medicine, and, eventually, nuclear weapons. Many scientists struggled with the realization that knowledge acquired through decades of peaceful investigation could also become an instrument of unprecedented destruction. Einstein watched these developments with growing concern. Although he had supported warning the American government about the possibility of a German nuclear program, he never celebrated the emergence of nuclear weapons. Like many scientists of his generation, he understood that humanity had crossed a threshold from which there would be no easy return. Scientific knowledge could no longer be separated from global political responsibility because the consequences of technological progress had become too immense to ignore. When the war ended after the atomic bombings of Hiroshima and Nagasaki, Einstein responded not with triumph, but with deep reflection. The conflict had demonstrated both the extraordinary power of modern science and the equally extraordinary danger that accompanied it. Questions that had once belonged primarily to physicists now belonged to diplomats, political leaders, philosophers, and ordinary citizens, because the future of civilization itself had become connected to decisions about technologies born from scientific discovery. The final decades of Einstein's life were therefore shaped
not only by equations and theoretical investigations, but also by an increasingly urgent effort to encourage international cooperation, reduce the risk of future wars, and remind the public that scientific progress without wisdom could never guarantee a safer world. His voice, once known almost exclusively within physics, gradually became one of the most recognizable moral voices of the 20th century, even as he continued searching for the deeper mathematical order that he believed still lay hidden beneath the universe. The years following the Second World War brought Einstein a different kind of responsibility, one that he had never actively sought but could no longer avoid. By then, he had become far more than a theoretical physicist. To millions of people around the world, his name had become synonymous with science itself, and every public statement he made attracted attention far beyond the scientific community.
Journalists sought his opinion not only on physics, but also on international politics, education, civil rights, nuclear weapons, and the future of humanity. Einstein accepted that attention cautiously. He had always believed that scientists remained ordinary citizens with the same moral obligations as everyone else. Scientific expertise did not automatically make someone wiser in political matters. Yet he also felt that those who understood the consequences of modern technology had a responsibility to explain those consequences honestly. Remaining silent simply because a subject extended beyond the laboratory no longer seemed acceptable in a world capable of destroying itself. Nuclear weapons remained at the center of his concerns. The destruction of Hiroshima and Nagasaki had demonstrated that the theoretical relationship between mass and energy was no longer merely an elegant equation appearing in scientific journals.
It had become part of a new geopolitical reality in which a single weapon possessed destructive power beyond anything previous generations could have imagined. Einstein feared that if international rivalries continued unchanged while military technology advanced ever further, humanity might eventually create circumstances from which no nation could emerge victorious. Rather than arguing that scientific research itself should stop, he urged political leaders to recognize that technological progress had fundamentally changed the conditions under which nations interacted. Diplomatic failures that once produced conventional wars could now threaten civilization on a global scale. Preventing future catastrophes, therefore, required more than stronger weapons. It required stronger international institutions, greater cooperation between nations, and a willingness to resolve conflicts before they reached the point where military force became the only remaining option. These views did not always make Einstein popular. Some critics considered him overly idealistic, while others believed he underestimated the realities of international politics during the rapidly developing Cold War. Einstein understood that simple solutions did not exist. Nevertheless, he remained convinced that the destructive potential created by modern science demanded an equally serious effort to strengthen international cooperation. In his view, technological progress had outpaced humanity's political institutions, leaving civilization with extraordinary new powers, but without equally effective mechanisms for managing them responsibly. Alongside these public concerns, Einstein continued pursuing the scientific problem that had occupied him for much of the final part of his career. He remained fascinated by the possibility of a unified field theory capable of describing gravity and electromagnetism within a single mathematical framework.
Every morning he returned to his office at the Institute for Advanced Study, filled notebooks with equations, reconsidered old assumptions, and searched for relationships that might reveal a deeper level of order beneath the theories already known. Many colleagues regarded the search with increasing skepticism. Physics was moving in different directions. Quantum electrodynamics achieved remarkable predictive success. Particle physics expanded rapidly through both theoretical advances and increasingly powerful experiments. Entirely new research programs emerged, attracting younger scientists whose interests differed substantially from Einstein's. He watched these developments with genuine admiration for their technical achievements, yet he never abandoned his conviction that an even more comprehensive description of nature remained possible. To many observers, this persistence appeared stubborn, but it reflected a pattern that had defined his thinking since childhood.
Einstein had always been willing to spend years pursuing questions that others considered too speculative or too difficult, believing that nature often rewarded patience more generously than speed. Whether the search succeeded became, in a sense, less important than the example it provided. Scientific history is often remembered through discoveries, yet discoveries themselves usually emerge from much longer periods filled with uncertainty, failed approaches, abandoned calculations, and ideas that ultimately lead nowhere. Einstein experienced those frustrations just as every other scientist did. The difference was that the magnitude of his earlier successes sometimes encouraged people to imagine that every thought he pursued must inevitably transform physics once again. Reality was far more human. Some of his later projects failed to produce the unification he hoped to achieve. Certain criticisms he directed toward quantum mechanics did not ultimately prevail as experimental evidence accumulated. Younger researchers solved problems that had resisted previous generations, while other questions remained unanswered despite decades of effort. Einstein accepted these disappointments without losing the habit that had guided him throughout his life. Whenever one path reached a dead end, he simply returned to the underlying question and tried to approach it from another direction. Friends and visitors often remarked that despite his worldwide fame, daily life around him remained surprisingly ordinary. He enjoyed long walks through Princeton. He continued playing the violin, not as a public performance, but as a source of personal satisfaction. He welcomed conversations with students, colleagues, and visitors who wished to discuss science, philosophy, or politics, frequently allowing those discussions to continue far longer than anyone had originally intended.
Although photographs often emphasized his unruly hair and informal clothing, people who spent time with him usually remembered something else more vividly: the extraordinary patience with which he considered difficult questions before offering an answer. That patience had become one of the defining characteristics of his intellectual life. Einstein rarely rushed toward conclusions simply because they seemed attractive. He preferred to examine every assumption carefully, searching for hidden contradictions that others might overlook. Sometimes that approach carried him toward revolutionary discoveries. At other times, it led him into debates that remained unresolved throughout his lifetime. In either case, the method remained remarkably consistent. Understanding began not with certainty, but with the willingness to keep asking better questions. As the 1950s progressed, Einstein's health gradually declined, although he continued working almost until the end of his life.
Even while growing physically weaker, he remained intellectually engaged, filling pages with calculations and corresponding with scientists around the world. The questions that had fascinated him for decades still occupied his thoughts. And although he knew that many might never be answered during his lifetime, he showed little interest in abandoning them simply because success had become uncertain. The final chapter of Einstein's story would therefore be shaped not by one last revolutionary discovery, but by something perhaps even more enduring. The example of a scientist who never lost the curiosity that had first awakened when a small magnetic compass revealed that invisible forces could govern the visible world. Einstein's final years unfolded with remarkable consistency. Although his body gradually slowed, the habits that had shaped his entire life changed very little. He continued walking to his office at the Institute for Advanced Study whenever his health allowed, filled notebooks with calculations, exchanged letters with colleagues across the world, and devoted countless hours to questions that many younger physicists had already set aside. He never seemed particularly troubled by the possibility that he might not live long enough to solve them. For him, the value of scientific work had never depended solely upon reaching the final answer. It also depended upon asking questions carefully enough that future generations would know where to continue the search. His office reflected that philosophy. Visitors expecting an elaborate laboratory often found a surprisingly modest workspace filled with papers, books, handwritten equations, correspondence, and the familiar signs of a scientist who cared far more about ideas than appearances.
Einstein had spent decades becoming one of the most recognizable people on Earth. Yet fame had never fundamentally altered the way he approached his work. Celebrity existed outside the office door. Inside, there were only mathematical problems that either made sense or refused to do so. Even as medicine advanced rapidly during the middle of the 20th century, Einstein's own health gradually became more fragile. Doctors monitored an enlargement of his abdominal aorta, a condition that had already required surgical treatment several years earlier. They understood that the weakened blood vessel carried a serious risk, but treatment options remained limited compared with those available today. Einstein knew the nature of his illness and understood that it could eventually become fatal. Rather than allowing that knowledge to dominate his final years, he continued living according to the same routines that had guided him for decades. In April of 1955, the condition worsened suddenly. After experiencing increasing pain, Einstein was admitted to Princeton Hospital, where physicians determined that the abdominal aortic aneurysm had ruptured. Surgery might have prolonged his life for a short time, but it could not offer a permanent cure. Einstein made his decision with characteristic clarity. He declined further major intervention, explaining that he did not wish to prolong life artificially when its natural course had reached its conclusion. Throughout his career, he had accepted that every physical process, from the motion of galaxies to the beating of a human heart, ultimately belonged to the same universe governed by natural laws. His own mortality, painful though it might be, seemed to him no exception. Even during his final hours, his attention remained fixed on unfinished work. Papers covered with equations accompanied him to the hospital, and he continued making notes while he still possessed the strength to do so. Friends and colleagues later reflected that this detail captured something essential about his character. Einstein never regarded scientific inquiry as a profession that ended when office hours were over. It had become the natural way in which he engaged with the world. He died during the early morning of April 18, 1955, at the age of 76. With his death, physics lost one of its most influential thinkers, but the questions he had raised remained very much alive. Some had already transformed science beyond recognition. Others continued guiding research decades later, while a few still resist complete answers, even in the 21st century. The history of Einstein's ideas did not end with his life. General relativity became an essential part of modern astronomy, cosmology, and space exploration. Satellites providing global navigation must account for relativistic effects in order to maintain their extraordinary accuracy. Without those corrections, positioning errors would accumulate rapidly, eventually rendering modern navigation systems unreliable. What once appeared to be an abstract theory concerning the geometry of spacetime gradually became an indispensable part of everyday technology. Astronomers also continued testing general relativity under conditions far more extreme than Einstein himself
could ever have observed. The expansion of the universe, first established through astronomical observations during the 20th century, transformed cosmology into a precision science. Compact objects such as neutron stars provided natural laboratories where gravity reached extraordinary strengths.
Decades after Einstein's death, observations of binary pulsars revealed the subtle energy loss expected from gravitational radiation, offering powerful support for one of the theory's most remarkable predictions. The most dramatic confirmation arrived in the 21st century. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, directly detected gravitational waves produced by the collision of two black holes more than 1 billion light-years away. Einstein himself had predicted the existence of these waves as a consequence of general relativity, although he sometimes questioned whether they would ever be measured because the effect appeared unimaginably small. A century after the publication of his theory, instruments of extraordinary precision finally observed tiny distortions in spacetime passing through Earth, opening an entirely new way of exploring the universe. Black holes followed a similar path.
When Einstein completed general relativity, they existed only as mathematical possibilities emerging from the equations. Many physicists, including Einstein himself at various points, remained cautious about interpreting those solutions as descriptions of real astronomical objects. Over the following decades, however, theoretical work and increasingly sophisticated observations demonstrated that black holes are genuine features of the universe. In 2019, astronomers even produced the first image of the shadow surrounding a supermassive black hole, providing another striking illustration of how ideas that once seemed almost unimaginable had become observable reality. Quantum physics also continued developing in ways that Einstein could never have anticipated. Although experiments generally favored quantum mechanics over the deterministic picture he had hoped to preserve, the questions he raised about entanglement, locality, and the meaning of physical reality never disappeared. Instead, they inspired generations of physicists to investigate the foundations of quantum theory with increasing sophistication, ultimately contributing to fields such as quantum information science, quantum communication, and quantum computing. Even where Einstein's expectations proved incomplete, his insistence on conceptual clarity continued driving scientific progress. Looking back across the arc of his life, a striking pattern becomes impossible to ignore. The child fascinated by a compass, the student imagining what it would be like to chase a beam of light, the patent examiner questioning the nature of time, the physicist redefining gravity, and the elderly scientist searching unsuccessfully for a unified theory were never truly different people. At every stage, Einstein approached the universe in essentially the same way. He began with an observation that most people accepted without hesitation, questioned the hidden assumptions beneath it, and followed the consequences wherever they happened to lead, even when they challenged ideas that had seemed unquestionable for centuries. Perhaps that is the most enduring lesson of Einstein's life. His greatest contribution was not a single equation, a single theory, or even a single scientific revolution. It was the demonstration that genuine curiosity requires unusual patience. Revolutionary discoveries rarely begin with extraordinary answers. More often, they begin with ordinary questions that someone refuses to abandon simply because everyone else believes they have already been answered. The universe that inspired Einstein has not become less mysterious since his lifetime.
If anything, every major discovery has revealed still deeper questions about dark matter, dark energy, black holes, quantum gravity, the origins of spacetime, and the ultimate structure of physical law. The horizon of knowledge continues moving farther away each time science advances, reminding us that understanding is never a destination permanently reached, but a journey that continually opens new paths. When Einstein first watched the needle of a small compass turn toward the north, he realized that invisible forces could shape the visible world. That simple childhood experience eventually led him to transform humanity's understanding of space, time, gravity, light, and the structure of reality itself. More importantly, it demonstrated that the greatest scientific revolutions do not begin with certainty. They begin with the quiet decision to keep asking one more question after everyone else has become satisfied with the answers they already have.
One reason Einstein's story continues to resonate so deeply is that it does not follow the pattern we often expect from biographies of great scientists. Looking backward, it is tempting to imagine a life moving steadily toward inevitable success, as though every childhood experience pointed directly toward relativity, and every setback merely delayed an outcome that history had already decided. The historical record tells a far more interesting story. Einstein's achievements emerged from uncertainty, persistence, fortunate encounters, disappointing failures, supportive friendships, and years spent wrestling with questions that resisted solution long enough for many other people to have abandoned them. That perspective also changes the way we think about scientific progress itself. Modern discoveries are sometimes presented as a sequence of dramatic breakthroughs, in which one brilliant individual suddenly replaces an old worldview with a completely new one. Reality is almost always more gradual. Every scientific revolution grows from generations of earlier work, and every new theory inherits both the achievements and the unanswered questions of those that came before. Einstein admired Isaac Newton precisely because Newton had revealed an astonishing degree of order within nature. He admired James Clerk Maxwell because Maxwell unified electricity, magnetism, and light through a single mathematical framework. He admired Michael Faraday because Faraday's physical intuition transformed invisible fields from abstract ideas into central features of physics. Einstein did not erase their accomplishments, he extended them. The same pattern continued after Einstein's own discoveries. General relativity did not eliminate Newtonian mechanics. Engineers still rely on Newton's equations whenever they design buildings, bridges, aircraft, or machinery, because those equations describe ordinary conditions with extraordinary accuracy. Quantum mechanics did not make relativity obsolete, nor did relativity replace quantum physics. Each theory explains a different aspect of nature with remarkable success, while the search for a deeper framework capable of uniting them remains one of the greatest challenges in modern science. In that sense, Einstein occupies a fascinating position within the history of ideas. He transformed physics so profoundly that nearly every branch of modern science bears traces of his influence. Yet, one of the central problems that occupied his final decades remains unsolved. Physicists still seek a theory capable of reconciling general relativity with quantum mechanics under the most extreme conditions, such as those that existed during the earliest moments of the universe or deep inside black holes. String theory, loop quantum gravity, and several other approaches all represent attempts to address this challenge, but no single framework has yet achieved universal acceptance or received decisive experimental confirmation. Einstein would probably have found that situation entirely familiar. Throughout his career, he repeatedly demonstrated that unanswered questions should not be regarded as failures, but as invitations to look more carefully at the assumptions hidden beneath existing knowledge. Every time science reached what appeared to be a solid foundation,
He asked whether that foundation itself required closer examination. Sometimes the answer proved to be no. Sometimes it changed physics forever. Perhaps that habit explains why Einstein remains such an enduring symbol of curiosity. His image has become so recognizable that it is easy to forget what actually distinguished him from many other brilliant scientists.
It was not an extraordinary memory, an ability to perform impossible calculations in his head, or some mysterious form of intuition unavailable to everyone else. Those qualities have often been exaggerated by popular culture. What repeatedly appears throughout his letters, notebooks, conversations, and scientific papers is something much quieter. An unusual willingness to remain with a difficult problem long after the excitement of novelty had disappeared. Many people enjoy asking interesting questions. Far fewer possess the patience to spend years searching for answers that may never come. Einstein did. The thought experiment involving a beam of light accompanied him from adolescence into adulthood, before it finally became the foundation of special relativity. The search for a theory of gravity required nearly a decade of sustained effort before general relativity emerged in its complete mathematical form. His pursuit of a unified field theory lasted for decades without producing the breakthrough he hoped to achieve. Yet he continued working because he believed the question itself remained important, regardless of whether he personally would solve it. There is another lesson hidden within his story, although it is one that receives far less attention than the famous equations. Einstein's greatest discoveries rarely began with mathematics. They began with careful observation, conceptual clarity, and the discipline to define familiar ideas precisely before attempting to explain them. He repeatedly asked what scientists actually meant by words such as time, simultaneous, motion, measurement, and gravity. Once those concepts became sufficiently clear, the mathematics followed naturally as the language required to express relationships that had already become visible through careful reasoning. This approach continues influencing science today.
Whether researchers investigate black holes, quantum computers, gravitational waves, artificial intelligence, or the origins of the universe, progress rarely comes from accumulating isolated facts alone. It comes from recognizing patterns, questioning assumptions that have become so familiar they are no longer noticed, and remaining willing to reconsider ideas that once seemed completely obvious. That process has no final chapter. Every generation inherits questions from the one before it, while leaving new questions for those who follow. Einstein inherited unresolved problems from Maxwell, Boltzmann, Lorentz, Planck, and many others. Today's physicists inherit unresolved problems from Einstein. Future scientists will almost certainly inherit mysteries that have not yet even been recognized. Because every important discovery changes not only the answers we possess, but also the questions we know how to ask.
Perhaps that is why Einstein's life still feels surprisingly modern, despite the passage of more than a century. The technologies surrounding us have changed almost beyond recognition. Humanity has walked on the moon, photographed black holes, detected gravitational waves, mapped the cosmic microwave background, and begun building quantum computers. Yet the intellectual attitude that made those achievements possible remains remarkably similar to the one that first appeared in a curious child holding a simple magnetic compass. Wonder, patience, and the refusal to believe that familiar explanations must always be the final ones. Those qualities mattered when Einstein looked at a compass needle turning toward the north. They mattered when he imagined chasing a beam of light. They mattered when he questioned the nature of time, reimagined gravity as geometry, and challenged the foundations of quantum mechanics.
They continue to matter today because every major scientific advance begins in exactly the same place. Not with certainty, but with the willingness to ask a question that other people have stopped asking. The universe has changed remarkably little since Einstein's lifetime. The stars still burn through nuclear fusion. Gravity still shapes galaxies. Light still crosses the enormous distances between worlds. Time still flows according to the same physical laws, whether anyone notices them or not. What has changed is our understanding of those phenomena, and much of that transformation can be traced back to one individual who refused to accept that the deepest mysteries of nature had already been solved. That is why Albert Einstein's legacy cannot be measured only by the theories he created or the equations that now appear in textbooks around the world. His greatest legacy lies in demonstrating that genuine scientific progress begins with intellectual honesty, grows through relentless curiosity, and depends upon the courage to follow evidence wherever it leads, even when the destination overturns ideas that humanity has accepted for centuries. And perhaps the most remarkable aspect of that legacy is that the journey remains unfinished. Somewhere, at this very moment, another student is asking a question that appears too simple to matter. Another researcher is noticing a contradiction that everyone else has learned to ignore. And another generation is preparing to discover that the universe is still far stranger, richer, and more beautiful than we currently understand. That possibility, more than any single equation, is the lasting gift of Einstein's life. If Einstein could see the scientific world today, he would almost certainly recognize many of its questions, even if he found the technology almost unimaginable.
Giant observatories now study galaxies whose light began its journey billions of years before the Earth existed. Spacecraft travel beyond the outer planets, carrying instruments capable of making measurements that would once have belonged entirely to science fiction. Particle accelerators recreate conditions that existed only fractions of a second after the birth of the universe, while atomic clocks have become so precise that they can detect tiny differences in the flow of time caused by changes in altitude, measured in mere inches. Yet, despite these astonishing achievements, modern physics remains unfinished. Astronomers have concluded that the matter we can actually see, stars, planets, gas clouds, and galaxies, accounts for only a small fraction of the universe. The remaining mass appears to exist in a form that neither emits nor reflects light, revealing itself only through its gravitational influence. This unseen component has become known as dark matter, but the name itself is not an explanation. It is simply a label describing something whose true nature remains unknown. An equally profound mystery surrounds the expansion of the universe. Toward the end of the 20th century, astronomers discovered that distant galaxies are not merely moving away from one another. The expansion itself is accelerating, as though space is being driven apart by an unknown phenomenon that current physics cannot yet explain completely. Scientists refer to this effect as dark energy, although, once again, the term identifies the observation rather than providing its ultimate cause. These discoveries remind us of something Einstein understood throughout his career. Giving a mystery a name is not the same as understanding it. A word may organize our knowledge, but it cannot replace an explanation. The same lesson appears again and again throughout the history of science. People once spoke confidently about gravity, without understanding why masses attracted one another. They described electricity long before they understood electromagnetic fields. They observed light for thousands of years before realizing that it obeyed principles unlike anything human intuition had imagined. Every generation inherits mysteries that initially appear impossible. Then, little by little, those mysteries become ordinary knowledge. At the same time, each answer uncovers questions that no one had previously known to ask. Einstein experienced that pattern repeatedly. Special relativity resolved the contradiction between mechanics and electromagnetism, but it immediately raised deeper questions about gravity. General relativity explained gravity in a completely new way. Yet it left unresolved the relationship between gravitation and quantum physics.
Quantum mechanics achieved extraordinary predictive success, but it introduced conceptual puzzles that continue inspiring research today. Scientific progress has therefore never resembled the construction of a finished building. It is much closer to walking across an endless landscape. Every hill that is climbed reveals a wider horizon beyond it. That image captures Einstein's life remarkably well. He never behaved as though science were approaching its conclusion, even after publishing theories that transformed humanity's understanding of reality. He continued searching, because he believed nature possessed a deeper coherence that remained hidden beneath existing knowledge. Whether or not that conviction ultimately proves correct, the attitude itself has become one of his greatest intellectual legacies. Perhaps this explains why Einstein continues to fascinate people who have little interest in advanced mathematics. His story is not fundamentally about equations. It is about curiosity, disciplined by patience. It is about refusing to confuse familiarity with understanding. It is about recognizing that the world often appears obvious only because we have grown accustomed to questions we stopped asking long ago. The child holding a compass, the student imagining a race with a beam of light, the patent examiner reconsidering the meaning of time, and the elderly physicist searching for a unified description of nature were all guided by exactly the same habit of mind. Whenever everyone else accepted an idea as self-evident, Einstein quietly asked a simple question: how do we actually know that it is true? That question changed physics. More importantly, it continues changing science, because every generation eventually discovers that some of its deepest assumptions are only temporary answers, waiting to be examined once again. Perhaps the next great scientific revolution has already begun in exactly the same way. Not with an enormous laboratory, not with an impossibly complicated equation, but with someone looking at an ordinary phenomenon, noticing a contradiction that everyone else has overlooked, and deciding not to let the question go. If Einstein's life teaches us anything, it is that the future of science rarely begins with certainty. It begins with curiosity strong enough to survive years of uncertainty, disciplined enough to question even the most familiar ideas, and patient enough to keep searching long after easier answers have become available. The universe has rewarded that kind of curiosity before. There is every reason to believe it will do so again. The story of Albert Einstein is often told as though it belongs to a single extraordinary individual whose brilliance permanently separated him from everyone around him. That interpretation is understandable, but it overlooks something essential. Einstein never worked outside the history of science. Every discovery he made emerged from conversations that stretched across generations, linking together the work of Newton, Faraday, Maxwell, Boltzmann, Lorentz, Planck, and countless others whose ideas provided the foundation upon which his own thinking could develop. Science advances in this way far more often than popular history suggests. Every important discovery changes the meaning of earlier discoveries, instead of replacing them completely. Newton did not become irrelevant when Einstein developed relativity. Maxwell did not disappear when quantum mechanics transformed our understanding of light. Instead, each generation revealed that nature possessed a richer structure than the previous generation had imagined, while preserving the insights that continued describing the world within their proper domains. This gradual expansion of understanding may be the most remarkable feature of scientific progress.
Human beings do not uncover reality all at once. They approach it layer by layer. Each generation inherits a map drawn by those who came before, corrects its mistakes, extends its boundaries, and leaves behind a slightly larger map for the next generation to continue exploring. No scientist, regardless of talent, ever reaches the final edge. Einstein understood this better than most. He often spoke with great admiration about Isaac Newton, describing him as one of history's greatest intellectual achievements, rather than someone whose work had simply become outdated. Newton had discovered laws capable of explaining an astonishing range of natural phenomena, and those laws remained extraordinarily accurate wherever the effects of relativity became negligible. Einstein's own theory did not destroy Newton's achievement. It explained why Newton's description worked so well, while revealing that an even deeper description became necessary under more extreme conditions.
The same relationship now exists between Einstein's work and modern physics. General relativity continues describing gravity with extraordinary accuracy across an immense range of astronomical situations. Yet physicists also recognize that it cannot represent the final word. Near the centers of black holes, during the earliest fractions of a second after the Big Bang, and at the smallest quantum scales, general relativity and quantum mechanics produce descriptions that remain difficult to reconcile within a single theoretical framework. This unresolved tension is one of the defining scientific challenges of our time. Researchers continue searching for a theory that preserves the remarkable successes of both relativity and quantum mechanics, while explaining how they emerge from a deeper and more comprehensive understanding of nature. Many promising ideas have been proposed, including string theory, loop quantum gravity, causal approaches to space-time, and several other mathematical frameworks. Each offers valuable insights, yet none has received the decisive experimental confirmation that would allow the scientific community to regard it as the long-awaited successor to our current theories. Einstein would almost certainly have recognized the situation immediately. Throughout his life, he believed that every successful scientific theory should eventually reveal an even deeper level of simplicity beneath apparent complexity. Whether that expectation ultimately proves correct remains uncertain, but the search itself continues, inspiring some of the most ambitious research programs in modern science. Perhaps that is the most enduring aspect of Einstein's legacy. His greatest contribution was never the encouragement to admire genius. It was the encouragement to trust careful reasoning more than familiar assumptions.
Again and again, he demonstrated that ideas appearing perfectly obvious could conceal hidden contradictions waiting patiently to be discovered. Space looked absolute until someone examined the meaning of simultaneous events. Gravity looked like an invisible force until someone asked whether free fall might reveal a different explanation. Quantum mechanics appeared incomplete to Einstein because he believed that understanding required more than successful calculation. And even though later experiments favored the standard quantum description, the questions he raised forced physicists to clarify their theories with far greater precision than would otherwise have been necessary. History rarely rewards unquestioning agreement. It rewards careful criticism directed toward the evidence itself. Einstein practiced that discipline throughout his life. He challenged established ideas when they no longer explained the observations.
He challenged his own conclusions whenever he found weaknesses in his reasoning. He challenged new theories, even after they became widely accepted, if he believed important conceptual questions remained unanswered. Sometimes those challenges transformed science. Sometimes they did not. In every case, they made scientific understanding stronger, because every serious criticism required equally serious answers. When people remember Einstein today, They often picture the familiar photograph of an elderly man with untidy white hair, thoughtful eyes, and an expression balanced somewhere between curiosity and quiet amusement. That image has become one of the most recognizable portraits of the 20th century, yet it represents only the final chapter of a much longer journey that began with a child wondering why a compass needle refused to point in random directions. Everything that followed grew naturally from that same instinct.
The student imagining what it would be like to travel beside a beam of light. The young patent examiner refusing to accept familiar definitions of time. The mature physicist replacing gravity with geometry. The older scientist questioning the philosophical foundations of quantum mechanics. The elderly researcher filling notebooks with equations while searching unsuccessfully for a unified theory. Across every stage of his life, the questions changed, the mathematics became more sophisticated, and the scientific consequences became increasingly profound. Yet the underlying habit of mind remained remarkably constant. He never stopped asking why. And perhaps that is why Albert Einstein continues speaking to every generation of scientists, students, and curious readers alike. The technologies surrounding us will continue changing. New theories will replace old ones, and discoveries that seem unimaginable today will eventually become ordinary knowledge.
Yet the process that makes those discoveries possible will remain fundamentally the same. It will begin with someone willing to look at an ordinary phenomenon, notice a contradiction that others have overlooked, question an assumption that everyone else has accepted, and continue searching patiently until a clearer understanding finally emerges. That quiet determination, more than any individual equation or scientific paper, is the true legacy of Albert Einstein. It reminds us that the universe has never stopped offering new mysteries to anyone willing to look closely enough, and that every answer worthy of lasting importance begins with the courage to ask one more question than anyone else thought necessary. At the same time, Einstein's life reminds us that science is not a collection of isolated facts waiting to be memorized, but an ongoing conversation that stretches across centuries. Every equation represents countless earlier questions. Every experiment stands upon generations of accumulated knowledge. Every breakthrough owes something to the work of people whose names may never appear in textbooks, yet whose ideas quietly became part of the intellectual foundation from which later discoveries emerged. Einstein himself often acknowledged this continuity, recognizing that his own achievements would have been impossible without the scientists who had spent decades, and in some cases, centuries, building an increasingly accurate picture of the physical world. This perspective is especially important because history has a tendency to simplify extraordinary lives into myths. The popular image of Einstein often suggests that he worked in complete isolation, producing revolutionary ideas through sudden flashes of inspiration that arrived almost effortlessly. The historical record reveals something far more instructive.
His notebooks contain abandoned calculations, crossed-out pages, revised assumptions, and repeated attempts to solve problems that resisted every approach he could imagine. Letters exchanged with colleagues reveal long discussions, disagreements, requests for criticism, and careful reconsideration of ideas that initially seemed convincing. His greatest achievements were not moments of effortless brilliance, but the result of extraordinary persistence applied over many years. That distinction matters because it changes what success in science actually looks like. Scientific progress is rarely driven by people who never encounter difficulty. It is driven by people who continue thinking carefully after difficulty appears. Einstein possessed an unusual ability to remain intellectually patient. When a problem refused to yield an answer, he did not immediately conclude that the question had been poorly chosen. Instead, he often assumed that some hidden assumption still required examination.
Sometimes that assumption concerned mathematics. Sometimes it concerned physical intuition. Sometimes it involved concepts that scientists had accepted for generations without realizing they contained subtle contradictions. His work on simultaneity illustrates this habit perfectly. Countless physicists before Einstein had measured time with remarkable precision. Yet almost no one had stopped to ask exactly what it meant for two distant events to occur at the same moment. The concept appeared so obvious that it seemed unnecessary to analyze. Einstein recognized that the apparent simplicity of the idea concealed a profound difficulty. Once that hidden assumption became visible, an entirely new understanding of space and time emerged almost inevitably from the effort to define the concept consistently. The same pattern appeared again during the development of general relativity. For centuries, gravity had been described successfully as a force acting across space. Einstein asked whether that description reflected physical reality or merely an approximation that worked under ordinary conditions. By replacing force with the geometry of space-time, he transformed one of the oldest subjects in physics without changing the observable facts that earlier scientists had already explained. The falling apple still fell. The moon still orbited the Earth. The planets still circled the sun. What changed was humanity's understanding of why those motions occurred. Perhaps this is why Einstein's work continues to feel surprisingly modern, despite the passage of so much time. His theories answered some of the greatest scientific questions of the 20th century. Yet they also demonstrated that every answer creates new questions whose existence had previously remained invisible. Before special relativity, physicists struggled to reconcile mechanics with electromagnetism. Before general relativity, gravity appeared fundamentally understood. Before the debates over quantum mechanics, many researchers believed they were approaching a nearly complete description of the microscopic world. Each apparent conclusion eventually became the beginning of an entirely new chapter. That process has never stopped. Modern physicists continue investigating questions that would have fascinated Einstein. What is the true nature of dark matter? Why is the expansion of the universe accelerating? Can gravity ultimately be described within a quantum framework? What happened during the earliest moments after the Big Bang? Are space and time themselves fundamental features of reality? Or do they emerge from something even more basic? No one yet possesses complete answers. In many ways, that uncertainty represents one of science's greatest strengths, rather than one of its weaknesses. Scientific knowledge does not become valuable because it claims certainty about everything.
It becomes valuable because it provides increasingly reliable explanations while remaining willing to revise them whenever new evidence demands it. Einstein understood this principle better than almost anyone. He challenged accepted theories when observations required it, but he also expected his own ideas to face the same standard. No scientific theory deserved protection simply because it had become famous. Every explanation ultimately remained accountable to nature itself. That intellectual humility often disappears from popular accounts of Einstein's life. People understandably celebrate the brilliance of his discoveries, yet they sometimes overlook his willingness to admit uncertainty whenever evidence remained incomplete. Even during his disagreements with quantum mechanics, he acknowledged the extraordinary predictive success of the theory. His objections concerned its conceptual interpretation rather than the remarkable accuracy of its calculations.
Although history eventually favored the standard quantum framework in many respects, the philosophical questions he raised continued shaping research into the foundations of quantum theory for decades afterward. The measure of a scientist, therefore, is not simply the number of correct answers they produce. It is also the quality of the questions they leave behind. By that standard, Einstein's influence remains extraordinary. Many of the deepest problems explored by contemporary theoretical physics still bear the imprint of questions he asked nearly a century ago. Researchers continue debating the relationship between gravity and quantum mechanics, the structure of spacetime, the nature of cosmological expansion, and the search for a unified description of the fundamental interactions. Even where modern science has moved beyond Einstein's own expectations, it has often done so by following paths that his questions first helped illuminate. For that reason, Albert Einstein's story should never be understood merely as the biography of a remarkable individual. It is also the story of how human curiosity evolves across generations, how ideas mature through criticism and refinement, and how the search for understanding continually reshapes the way civilization sees itself. His life demonstrates that the greatest scientific revolutions rarely arrive because someone possesses supernatural intelligence. They emerge because someone remains willing to question familiar assumptions with unusual patience, follow evidence with unwavering honesty, and continue searching long after easier explanations have become comfortable enough for everyone else to accept. If there is one final lesson to take from Einstein's life, it is that the history of science is ultimately a history of changing perspectives. The universe itself does not transform because human beings invent a new theory.
The stars continue burning, planets continue orbiting, light continues traveling through space, and gravity continues shaping the structure of galaxies exactly as it always has. What changes is our ability to recognize patterns that had been present all along, but remained hidden behind assumptions that seemed too obvious to question. That transformation of perspective is far more powerful than it first appears. When humanity learned that the Earth moves around the Sun rather than the other way around, the heavens themselves did not change. When Newton described gravity mathematically, apples did not begin falling differently. When Maxwell unified electricity and magnetism, light did not suddenly acquire new properties. In each case, nature remained exactly as it had always been. The revolution occurred within human understanding. Einstein belongs to that same tradition. He did not alter the universe. He altered humanity's picture of the universe.
The distinction may seem subtle, yet it lies at the heart of every scientific revolution. Scientific progress does not consist of replacing one reality with another. It consists of replacing one description with a better one that explains more observations with greater consistency, while revealing relationships that had previously escaped notice. Every successful theory expands the boundaries of understanding without claiming to possess the final truth, because history repeatedly demonstrates that even the most successful explanations eventually become part of an even broader framework. That realization encourages a different way of thinking about knowledge itself. People often imagine that science advances by collecting facts one after another until nothing remains unknown. Reality is considerably more interesting. Each important discovery increases the number of meaningful questions available to ask.
Before Einstein, few scientists wondered whether time itself depended upon the observer. Before general relativity, almost no one imagined that geometry could explain gravity.
Before quantum mechanics, the microscopic world appeared far less mysterious than it eventually proved to be. Knowledge does not simply eliminate mystery. Very often, it refines mystery into sharper and more productive forms. The questions become deeper because the understanding becomes deeper. Einstein recognized this throughout his career. He never expected the universe to become simple merely because human mathematics became more sophisticated. Instead, he believed that every genuine advance should reveal a more coherent picture, while simultaneously exposing new layers of reality waiting to be explored. That expectation has repeatedly been confirmed by the history of modern physics.
Every major breakthrough has solved problems that once seemed impossible, while uncovering entirely new mysteries that previous generations could not even have imagined. Perhaps that is why Einstein's work continues to inspire scientists far beyond the field of physics. His methods are not limited to relativity or cosmology. They represent a broader intellectual discipline founded upon careful observation, logical consistency, conceptual clarity, and the willingness to reconsider ideas that have become so familiar they appear unquestionable. Whether someone studies biology, chemistry, geology, mathematics, computer science, medicine, economics, or engineering, the same underlying principles remain remarkably similar. Progress begins when familiar assumptions are examined carefully enough for hidden inconsistencies to become visible. Einstein also reminds us that intellectual courage often appears much quieter than popular culture suggests. It is rarely dramatic.
It usually consists of continuing to think carefully when uncertainty becomes uncomfortable, resisting the temptation to accept convenient explanations before they have earned confidence, and remaining willing to admit that a cherished idea may require revision if observations refuse to support it. Those habits seldom attract immediate attention, yet they form the foundation upon which lasting scientific progress depends. Looking across more than a century since the publication of the Miracle Papers of 1905, it becomes increasingly clear that Einstein's greatest influence extends beyond any individual equation or theory. His work reshaped astronomy, cosmology, particle physics, space exploration, precision measurement, satellite navigation, and countless other disciplines. More importantly, it reshaped the questions scientists considered worth asking.
Entire fields of research that define modern physics exist because Einstein demonstrated that apparently settled problems could conceal revolutionary possibilities. That influence continues growing rather than diminishing. Each new generation tests general relativity under more extreme conditions, explores quantum phenomena with greater precision, constructs more sensitive observatories, and develops mathematical tools that Einstein himself never possessed. Some of those investigations strengthen his conclusions. Others reveal limitations that point toward theories still waiting to be discovered. Both outcomes represent success because science advances through explanation and correction together, rather than through unquestioning agreement. In that sense, Einstein's life offers an unusually hopeful vision of human knowledge. The universe is not becoming smaller because science explains more of it, it is becoming larger.
Every answer expands the horizon, beyond which still greater questions remain waiting, reminding us that curiosity is not a temporary stage preceding certainty, but a permanent companion to understanding itself. The closer humanity comes to comprehending nature, the more clearly it recognizes the extraordinary richness of everything that still lies beyond present knowledge. And so, the story that began with a curious child staring at the silent movement of a compass needle ultimately becomes something much larger than the biography of a single scientist. It becomes the story of humanity's endless attempt to understand the universe it inhabits. An attempt carried forward not by certainty, but by imagination, disciplined through evidence, by skepticism balanced with wonder, and by generations of people willing to devote their lives to questions whose answers may not arrive until long after they themselves are gone.
Albert Einstein became one of the greatest scientists in history because he transformed the way humanity thinks about space, time, gravity, light, and reality itself. His deeper legacy, however, reaches beyond physics. It reminds us that every generation inherits a universe that appears familiar until someone asks a question no one else thought to ask, and that the future of human knowledge will always belong to those who possess the patience to follow that question wherever it leads. There is something quietly beautiful about the way Einstein's story comes full circle. When we first met him, he was not standing before a blackboard covered with equations or addressing audiences around the world. He was a small boy, holding an ordinary magnetic compass in his hands, watching a needle move toward the north for reasons he could neither see nor explain. It was an experience so simple that millions of children have shared it before and since. Yet for Einstein, it revealed something that would shape the rest of his life. The universe was not limited to what human senses could immediately perceive. Beneath ordinary experience existed invisible structures, hidden relationships, and deeper laws waiting patiently to be discovered. Everything that followed can be understood as an attempt to answer the question that Compass first inspired. What invisible order governs the visible world? That question carried him through every stage of his life. It accompanied him as a student struggling with formal education, as a young graduate unable to secure an academic position, as a patent examiner imagining impossible journeys alongside beams of light, as a professor redefining gravity itself, and finally, as an elderly scientist searching for a deeper unity within the laws of nature. The specific problems changed. The mathematics became increasingly sophisticated. The scientific consequences grew beyond anything even he could have anticipated. Yet the underlying curiosity remained remarkably constant. It is tempting to imagine that Einstein eventually reached the answers he had spent his life seeking. In reality, the opposite is much closer to the truth. The longer he studied the universe, the more clearly he recognized how much remained beyond human understanding. When he developed special relativity, he uncovered entirely new questions about gravity. When he completed general relativity, the quantum world refused to fit comfortably beside it. When quantum mechanics matured into one of the most successful scientific theories ever created, it raised philosophical questions that continue challenging physicists today. Even his lifelong search for a unified field theory ended not with a final solution, but with an invitation for future generations to continue where he had stopped.
There is something profoundly encouraging about that. Modern culture often celebrates certainty. It rewards quick answers, confident opinions, and simple conclusions. Science, however, has always progressed in the opposite direction. Every genuine discovery begins by exposing the limits of what people previously believed they understood. Knowledge grows because someone becomes dissatisfied with explanations that everyone else has accepted, not because someone claims to possess all the answers. Einstein understood that better than almost anyone. He never confused confidence with certainty. He never assumed that a successful theory represented the final description of reality. He never believed that the universe owed humanity simple explanations. Instead, he trusted something far more reliable than certainty. He trusted that nature is internally consistent, that careful observation matters more than intuition, and that honest questions are often more valuable than premature answers.
That intellectual attitude remains one of his greatest gifts to science. Every modern physicist who studies black holes, gravitational waves, quantum information, the early universe, dark matter, or dark energy, continues participating in a conversation that Einstein helped reshape. Some of those researchers will confirm ideas he proposed. Others will eventually demonstrate that certain aspects of his theories require revision or extension. That possibility would not diminish his legacy. On the contrary, it would represent exactly how scientific progress is supposed to work. No great scientific theory survives because people admire its creator. It survives because nature continues agreeing with its predictions. And when nature eventually reveals something new, scientists must be willing to change their understanding once again. That principle connects Galileo to Newton. It connects Newton to Maxwell. It connects Maxwell to Einstein.
And one day it will connect Einstein to whoever uncovers the next great revolution in our understanding of reality. Perhaps that future scientist is alive today. Perhaps they are a child sitting in a classroom somewhere, becoming fascinated by an ordinary observation that everyone else has learned to ignore. Perhaps they are wondering why something behaves the way it does, asking questions that adults dismiss as too simple, or refusing to accept an explanation simply because it appears in a textbook. History suggests that scientific revolutions often begin exactly that way, not with extraordinary laboratories or impossible machines, but with ordinary curiosity, pursued more patiently than anyone else believes necessary. The remarkable thing about Einstein's life is that it reminds us genius is rarely a single moment of inspiration. It is a way of thinking. It is the willingness to remain curious after other people become comfortable.
It is the discipline to examine assumptions that appear obvious. It is the patience to spend years following a difficult problem without any guarantee that the search will succeed. And perhaps most importantly, it is the humility to accept that nature will always have the final word. Today, more than a century after a young patent examiner published 4 papers that transformed modern physics, spacecraft navigate the solar system using relativistic corrections. Astronomers observe black holes whose existence emerged naturally from equations that many once considered purely mathematical. Gravitational waves ripple through the fabric of space-time exactly as general relativity predicted. Quantum technologies continue developing from ideas that Einstein both advanced and challenged. Every one of these achievements serves as a reminder that abstract thought, when guided carefully by evidence, possesses the extraordinary power to reshape civilization.
Yet even after all those discoveries, humanity still stands where every generation has always stood, looking outward, looking inward, trying to understand a universe that remains larger, older, stranger, and more beautiful than any theory can fully capture. There are still questions without answers. There are still contradictions waiting to be noticed. There are still mysteries hidden beneath phenomena that appear perfectly ordinary. The compass needle still points north. The stars still shine overhead. Light still travels across unimaginable distances before reaching our eyes. Time still flows according to laws that challenge common intuition. The universe continues, inviting questions exactly as it did when a curious boy first wondered why an invisible force could move a small piece of metal enclosed inside a simple pocket compass. Albert Einstein spent his entire life accepting that invitation. He did not solve every mystery. No scientist ever will.
What he accomplished instead was something far more enduring. He showed that the universe becomes richer, not poorer, every time human beings ask deeper questions. He demonstrated that imagination and evidence are not opposing forces, but indispensable partners in the search for truth. He proved that even the most familiar aspects of reality
can conceal extraordinary secrets when viewed from a different perspective. And perhaps, as you look up at the night sky after hearing his story, that is the idea worth carrying with you. The universe has not finished revealing itself. Somewhere beyond the questions we can answer today are discoveries that will redefine tomorrow's understanding of space, time, gravity, matter, and reality itself. Those discoveries are waiting for minds willing to question familiar assumptions with honesty, patience, and curiosity, just as Albert Einstein did throughout his entire life. Because the history of science has never been the story of people who believed they already understood the universe. It has always been the story of those who looked at it one more time, asked one more question, and discovered that reality was even more astonishing than anyone had imagined.